Hello, everyone. I'm Naomi Ceder, and I guess I'm the one that gets to kick off the Manning Python Twitch conference today. Um, I'm the author of the Quick Python book, third edition. I'm the past chair of the Python Software Foundation, and I've been doing Python for nearly 20 years. So what I wanted to walk you through today was a little bit about something that's kind of fundamental to the way that Python thinks about code. And I call this, it really is easier to ask forgiveness than permission. And let's get into it, and you will see what I mean as we go on. So I am, in fact, a language nerd, and by that I mean human languages. Certainly computer languages, but human languages first. I've got a PhD in Greek and Latin. I've studied things like Sanskrit, Egyptian, various things like that along the way. These days, actually, I'm studying Spanish and Portuguese. So I've always been interested in the way languages work. And one thing I've learned from all of that is that languages have their own ways of doing things. And if you want an example of that, and it's also good fun, you can go and Google a site or actually search on YouTube for a YouTube channel called Google Translate Sings. The thing there is that there's a singer, and she is a good singer. But what she does is she takes popular song lyrics and runs them through Google Translate, I don't know, about 10 times from English to Spanish, Spanish to Japanese, Japanese to German, et cetera, et cetera, et cetera. And then she sings the result to the original tune. And as you can imagine, it's funny. It's darned entertaining. So the point there is that it's not just vocabulary that differs from a language. You can't just sort of translate the words one to one and come up with the same result. Every language has a way of thinking about things and expressing things that differs from language to language. And computer languages may not be as complex as human languages, but the same thing is more or less true. The structures of a programming language, in fact, control how you end up thinking about a problem. I mean, yes, in theory, you can do anything in one computer language that you can do in another computer language. But in practice, the way that you actually solve a problem, it depends upon how the language approaches situations like that. And in particular, the situation that I want to talk about is what happens when things go wrong. And we know from writing code that there is an endless variety of things that can go wrong whenever you try to write code. You can get bad values, you can have bad logic, you can have resources that are unavailable. It goes on and on and on, but there are other ways you can think of it. You can think of it as errors that occur at compile time, like syntax errors, or if you've got static typing, a type error, or runtime errors, like a resource maybe isn't available, or something from an external process, or if you've got dynamic typing, then type errors, I guess, fit there. Or you can think of it even differently still. You can think of there are errors that you can recover from and errors that you can't. So, for example, an unrecoverable error, a syntax error. There's really no point in trying to recover from that. Again, with type errors, that can be an unrecoverable error in a statically typed language. And on the other hand, you can have errors that maybe it is worth trying to recover from. Maybe a resource is temporarily unavailable. If you try again, you will get it. Maybe there's an external process that, again, if you repeat, you might be able to get a result. Just varying things. So there are a lot of ways, in other words, that you can think about about errors. And it stands to reason there are a lot of ways that a language can approach the question of handling errors. And I want to talk a little bit about just a few examples here. I'm not trying to critique these languages. I'm not even saying I've got an expert's version. I'm just sort of giving you some what strike me as common examples of the way some other languages have handled errors. So from back in the day, Perl, I always think of in my head as Perl as the do or die language, because back 20 years ago, I remember that it was quite common in Perl to see things like that, where you do the thing or die with an error message. In other words, end the program. Or you die with the error message unless you can do the thing. But, either way, you're going to die and you have a chance to spew the message. Now that's not the only way that Perl handles things, but that's one pattern that was very common. Or again, back from my days 20 years ago and more, C had a number of ways to handle possible error conditions. You might check to see if a pointer was null to see whether or not something worked. You might, if you had some types of operations, check for a global variable with the error number, and then you could decipher the error number and decide what to do. You could actually do something that was vaguely akin to handling an exception with setting a destination and jumping to it. Or, and I have to admit, in my C code, I think this was probably one of the ways that I ended up having my errors behave most often. You can get a seg fault. You overwrite a buffer, you start doing something that is just silly, and your computer crashes with a seg fault. C++, of course, advanced things quite a bit, and the C++ does have the idea of handling exceptions, but it also does a lot of look before you leap checking. That is, can we do this thing? Let's check this value. If this value is right, we can do the thing. If it isn't, we can't do the thing. So, it's got various ways of doing that, but you do have exceptions, although C++ in general is not, I don't think, at least in my experience, as heavy in using exceptions as some languages might be. You can also think about Java. And Java, again, is similar to C++ in that it has exceptions, but it also has a certain amount of what I would, again, call look before you leap checking. The other thing about Java exceptions that is interesting is that Java exceptions draw a distinction between checked or catch or specify exceptions and unchecked ones. So in this example here, the exception that we're dealing with is an IO exception. We've got some file reading that might throw an IO exception. This is one where it's a checked exception. Either you have to handle it inside this method, or you have to specify that your method throws IO exception. That is, you have to actually one way or another declare what you're going to do with that kind of exception. And then there are others, again, like maybe syntax errors or something like that don't have to have that requirement. Then JavaScript. JavaScript, as always, goes its own way. And JavaScript is a little bit different in that it's got 6 native exception types that can be raised either manually or through various conditions. But you can also throw any object, anything, as an exception. So you can throw an error, and that's fine, but you can also throw the value true. And then, you can go down and try to catch them. And in this particular case, you catch by matching the name to a value. So it's somewhat different again. Go Go can use this sort of two-channel way of handling errors where you have a variable that is returned and an error that is returned. So you've got two things, and then you can check the error value without worrying about what the return value is to detect an error. And sometimes you will see a pattern like this where you end up with the two of them sort of being checked back and forth. So it's a very, I guess I would say, a very explicit error pattern. Yeah, those are some of the ways that other languages do it. Of course, there are many more, and you can pick your own, and you can pick better examples. This is all just to kind of set the scene in a way. But I think my point is that they're all from languages that have sort of different constructs, different idioms, and each language kind of has its own way of doing it, and that tends to influence the way that you write code. So what about Python? That's the thing that I really want to talk about. Now, Python takes the approach of embracing rather than avoiding exceptions. And that is, in Python, we call this easier to ask forgiveness than permission, which is meant to be a contrast with look before you leap. And what we mean by easier to ask forgiveness than permission is that if you're going to do an operation, let's say it requires a sequence object, like say a for loop, rather than checking in advance to see if we've got a list type or a tuple type or various sequence types, in Python, the approach is to go ahead and do it. And if you have reason to worry about you're having the right type or not, then you can put in some code to handle the exception if in fact it's not the right type. So this works for Python for a few reasons. For one thing, it can make your code simpler and easier to read. And we do know that those of us in Python love to have readable code. Readability counts, as we say in the Zen of Python. Also, Python tends to use duck typing a lot. And in the off chance you're not familiar with the term, duck typing refers to the joke, if it walks like a duck and quacks like a duck, it's probably a duck. That is, if it will do the thing, we can go ahead and assume it's whatever type we need. And this is handy in Python, of course, because Python is not statically typed. I mean, it's a strictly typed language, but the assignment of types depends upon the objects, not the variables. So this is all sort of makes it somewhat easier to work in Python. Now, I don't want to spend a ton of time, but I do want to kind of quickly go through the basics of Python exceptions just to make sure that everybody's, had refreshed and we're all on the same page. So Python exception can have up to 4 parts. So there is a try block, which is the block of code doing the actual thing you want to do. Okay, there is an except block where you actually can specify the exception that you're looking for, and you can assign it to a variable. It's almost always E by convention. So this is just assigning the exception if we catch it to the variable E. And then, whatever code we want to do once we've caught that particular exception. You can also have an else block, and that block is executed if and only if there is no exception. So basically, you can get one or the other. You can get the except block or the else block. And of course, you can have more than one except block, but you will only ever get an else if no exceptions fire. And then you have a finally block. That is code that will always be executed. For example, if you're doing some exception checking about accessing a file, in the finally part, regardless of whether there's an error, you can put in code that will always close the file so that you don't have to worry about repeating the code, the close file code over and over again. And then, yes, you can always deliberately raise an exception, but it must be an exception type that you raise. And I'll show you this in a second. So as an example, and I'm just going to run this a few times to be sure that we're all familiar with how it works. So I've got a try block, an except block, an else, and a finally. And there's nothing fancy about this. If I run this, I get running code. I raised an exception, so I go to the exception block, and then I go to the this always executes in the finally. Okay. If on the other hand, I were to not raise that exception, it would do the other thing. It'd still run the code, but then I would not do anything there and get the else block instead. And then again, always the finally. So that's just kind of a quick refresher to make sure everybody's on the same page. So just a little background on this. Python has had exceptions as objects for over 20 years, since Python 1.5. The only in Python 3, only objects which are subclasses of base exception can be raised. If you try to raise true in Python, you'll be told that that's illegal. That won't compile, won't run. Most exceptions that are commonly used are subclasses of exception, which is an immediate child of base exception. You can do a bare except. If you are, that's just shorthand for saying except exception. I mean, that's what it's looking for. And then there are three others that are not subclasses of exception, but are subclasses of base exception. And that's system exit, exit generator, and keyboard interrupt. Those sorts of things, like if you're exiting the system, you wouldn't want to have a bare except trap that. Usually keyboard interrupt as well. You really don't, So in general, those are ones that do not inherit from exception. They inherit from base exception. And as we'll see, you can subclass everything so that you can be very precise and have your own custom array of exceptions if you want to catch very specific situations. So again, nothing special. You do this and without any handler, you will get, this is IPython's way of handling an exception traceback, but you can raise an exception. Not much to say there. As I mentioned, this exception class hierarchy, everything comes from base exception. And then we have 4 subclasses. It's generally frowned upon for user created or, anything not a core part of the language to inherit from base exception. If you've got a darn good reason, maybe, but in general, people will raise an eyebrow at that. So we've got 4 subclasses of base exception, as I mentioned: system exit, keyboard interrupt, generator exit. And then under exception, we have pretty much the world from import errors, importing file memory name error, file not found, value errors, type errors, and a bunch of warnings. So there's a wide variety of things that you can catch under that are all subclasses of exception. Now, subclassing exceptions is easy. So you can go ahead and have exceptions that are specific to a particular module, library, package, whatever you want. And this ability could certainly sometimes is useful. Particularly if you want to be able to localize something in something it's very complicated, it can be useful. You can also then, maybe it's something where you're in a long chain of function calls or classes or whatever. So subclassing is useful because it gives you more precision. And to show you what I mean by this, basically here I've done 2 special subclassed exceptions. So I made my special exception be a subclass of exception. I made my even more special exception be a subclass of my special exception that I just created. Now you'll notice to subclass an exception, all you need for the body is a pass. Because in general, and again, this would be something you would want to be very careful about ever doing. You'd need a really good reason. In general, we're not interested in messing with the machinery of an exception. We just want to have a specific type of exception. So if I do this, here I'm raising exception and I'm trapping exception. I do that, of course, it's going to trap it. If instead I decide I want to get my special exception, it's going to trap that. And again, you can kind of continue this on down. You get the idea. That is, since they're all children of exception, if I'm here trapping exception, that's what I'll always get. Now, on the other hand, if I decide to start trapping something like this, then it will trap exactly that class, yes. But if I decide to raise something that is not this class or a child of this class, in this case, I'm going to raise its immediate parent, it won't be trapped. And here then I'm back to just the default exception handling that IPython is giving me in my Jupyter notebook. So that's the basics of it here. Let me pause because I see I've got a question here. Do you think that in a function that can have optional return type, it is better to return a none or raising an exception? For example, a function gets something. Okay, personally, I think it is more Pythonic if you've got a function that may or may not return things, that I think it is more Pythonic to raise an exception rather than returning a none. If you have a function or a method that either returns a useful value or none, which is almost certainly not a useful value, you've in effect packed two messages into that return value. And the code that handles that on the other end is going to have to then have an extra step to handle that case of none. So rather than writing the code to handle that case of none, it probably makes more sense then to just have exception handling stuff. That's more, I think, in my opinion, more Pythonic. So good question. And I'll try to watch these as we go through. But we might end up having to leave them to the end because, well, sometimes when I get to talking, I don't pay attention to things. But I'll try to be watching for those. So, other question actually that I missed, slide deck be available. I will make sure that it's available on my GitHub. My username is Naomi Ceder, and I do have a repo for things. There is a version of this that is already available on the live streams repo on there. So if you go to Naomi Ceder and look around, you should be able to find pretty much this this deck or yeah, all of the same stuff in a Jupyter notebook, possibly more. Okay, so just kind of summing up here on the basics of exceptions. I would suggest that unless you've got something that is very complicated or very specific, you use built-in exceptions just because they're more universal and people are more likely to know what's going on, and you don't have to track importing them and things like that. But as with a lot of these things, it's kind of a trade-off. Maybe a specific exception makes your code more readable, not less. And on the other hand, maybe having your own giant hierarchy of custom exceptions means that there's a whole lot of messing around. You need importing the exceptions to be able to use them, and it makes your code a little bit more complicated. So you need to find a balance. It depends upon the situation. But here's what I'm talking about. It's so easy to make special exceptions that sometimes people will make special exceptions for everything they do. And then if I want to, I'm using my library and I know that it's going to catch this, and so they put in a whole sub-library of exceptions and whatever. Then if I want to actually trap those, I need to be sure that I'm importing all of those exception types to handle them. So that's the irritation that I find when people do complicated custom exception things. And things like ORMs and stuff like that are big on this. Then if I want to trap that specific exception, I need to go look up and make sure I can import it from the right place to use it. It's not a big deal. It's just a little bit of an irritation. So, as I say, it's a balance that everybody needs to strike, and your situation and I suppose your personal taste will depend on that. So again, Python's got a well-developed set of exceptions. They can be specific, and we can handle them in a hierarchy. This is all cool. And, I think as the style of Python, which is at least partly an interpreted language with dynamic assignment of variables and things like that, Python is a good language to use exceptions. And in fact, I would say that in general, exceptions are more Pythonic than doing a lot of checking. Did I get this result? Is this result null? Things like that kind of came up in the question earlier. Those, I think, are in general more Pythonic if you do them with exceptions rather than checking. Now, there are a couple of things to be cognizant of, to keep in mind. One of them is that you want to be sure the exception is something that is not going to be really, really, really common. If you expect the exception to happen, I don't know, say 50% of the time as you're going through a loop, then you might want to do some checking. You also want to be sure that you're checking for a particular and specific exception. Okay, trying to catch the world, as we'll see later on, isn't maybe the best thing. And again, does it make your code actually easier to read? Those are the things to keep in mind. Okay, so an example here of what I think is the difference. This is imaginary. I can't execute this code. It won't work. But it's to illustrate the sort of situation here. This is something that is designed to avoid exceptions. So this is really kind of in the look before you leap thing. So I've got, I don't know, it's a bunch of queries I'm going to run, or a bunch of items I'm looking for in a database. Who knows what it is? And I've got this database object that has a query and takes a parameter. And it has exactly this situation that was raised in the question before. If it doesn't get any results in its query, it returns null. None. So here I need to check, do I have, or at least it returns a false value, whatever it might be. I'm assuming it's none. So I need to check then to see if I actually have a result before I can find out how many rows I got in that query. Okay, and if it doesn't have anything, it's going to just skip on. Okay, this is avoiding handling things with exceptions. Now, I would argue that probably the more Pythonic way, certainly the easier to ask for forgiveness way, would be to do something like this. So here, I'm just going to go ahead and fire my query and print out its row count. Okay, if in fact it's a none, that is, I didn't get anything back, which is my other reasonable thing that I'm expecting here, and I try to do a count on a none object, it's going to give me attribute error. Nope, none does not have a count method. So I can do this then with the exception. I've got one less line of code, and it's, to me at least, a little bit clearer that this is the thing I'm doing. And this is the thing that handles the case that I don't expect to happen very often, but it could happen, and I just want to go right on by it. So that's an example of that. So now real quickly, I'm going to go through things that people do with exceptions that are not good, that are pitfalls, are bad examples. So we got bare accepts, too many accepts, too large a code block, and just not handling things well. And I want to give you some quick examples of this. Bare accepts, I told you before, they will catch all subclasses of exceptions. And that means they're all going to be handled the same way. So it's a pretty weird situation where every possible thing that could go wrong, you're going to do the same thing. Unless possibly it's just log it and then bail out of the program. Yeah, I could see that. But beyond that, you're not likely to want to handle everything that goes wrong in the same way. So, for example, this is just a very simple case here. And let me run it, and it wants an integer. So let me give it something that's not an integer. And it tells me it's an error. Okay, fine. But let me run that again. This time I'm going to give it an integer. Something went wrong. So again, an error entering the right format should never be confused with divide by 0. This is kind of a mindless, simple example to illustrate it. But actually, if you keep your eyes open in code review, you will occasionally find people trying to do similar things where it's sort of like a shortcut. They're thinking of the exception they expect, but they don't explicitly put it in on the except. So you want to be explicit there. As the Zen of Python says, explicit is better than implicit. Okay, another thing that sometimes people do is that they think if a few exceptions are good, a lot of exceptions are better, right? That can lead to code that's really hard to read and maybe not all that much more reliable than you had it to be in the first place. So here I've got an exception for keyboard interrupt. I've got an exception for a value error in trying to parse something that comes in for the line. And I've got around that an exception for file not found error. All of that stuff is fine, but in fact, the way that if you end up structuring code like this, it ends up being sort of cognitive overhead. It takes more time to parse and read as you try to source, as you try to get the sources of all of this stuff in your head and sort of like, okay, so I'm down here, so I got an exception. Where did that happen? Oh yeah, it must have been all the way at the top here. But in the meantime, we've got this. So again, it's something where you need to think about your situation and balance readability versus practicality. But again, I just want to be, point out that it's a good idea to think about this and not just load in lots of exceptions to catch every possible thing. And I suppose kind of the flip side is sometimes people will wrap just an enormous chunk of code in a try except block. And this is, well, again, it's legal, but what happens then is that you can end up with, we've got our try up here, and we've got a bunch of excepts down here that handle all the possible errors. That's fine. But as you read this code, if I think that I've got maybe a problem where I don't have enough parameters, is that handled down here? Actually, that's not even handled here. Wait a second. I can't open the file. Is that handled down here? See, basically, you again have this cognitive overhead of going back and forth between the exception handling block and your code block. So you want to think about that and structure things so that maybe if we're doing file not found and permission, we handle that up here where we're actually opening the file. Maybe we're doing some other stuff. We might want to handle that in another spot so that you don't have just a giant block of code that's trying to do everything. So let's see here. The last one, The last one prompts me to tell one of my favorite stories from teaching Python over nearly 20 years. And this actually happened, I think it was in the first year I was involved in teaching Python nearly 20 years ago. And it was at a high school. We started using Python and we made a Python elective. And a bunch of kids who'd taken other programming classes piled into the Python elective class because they thought it would be interesting and they liked it. And we had two guys that were working together that never could figure out what was wrong with their program. I happened to be sort of stopped by the classroom one day and they're like, come here. It doesn't do anything. What's wrong here? And the weird thing was their code never had an error, which would be good, right? Well, not so much, because basically what they were doing was pretty much every few lines they did something like this. That is, they did a try, and then they did some code, and then they did a bare except and pass. Now, those of you who've done much coding will see how funny this kind of is. Basically, the reason their code wasn't doing anything was that they had all sorts of exceptions and errors going on, but they had very carefully thrown all of that information away by just doing this except pass. In other words, try, if anything goes wrong, do nothing. That was all that they were doing. So once we got them sorted out and they came to terms with the fact they actually had errors, they managed to get their code to work. The point of this all is that except pass is something that you want to use very carefully. You never, almost never want except pass to make it into production code. It's great when you're sort of trying to figure out something and you know that, okay, here there's going to be a problem. I'm just going to ignore that for now until I get to the next problematic part. Maybe then, but it is just a very, very bad idea to do this. But occasionally you will see it. Okay, so let's go ahead. So again, things that you want to think about as you're using exceptions is how often are you going to get that exception? We'll talk a little bit about performance in a little while. If you get a lot of exceptions, like you've got a for loop where half of the time you're getting exceptions, that will be slow. You want to consider what you're looking for and how you're handling it. And as I say, maybe you want to use built-in exceptions rather than making your own custom exceptions. That's my prejudice. There are other people who argue equally strongly for having lots and lots of specific exceptions. But this is my talk, so I'm giving you my opinion. Okay, that's all of the ordinary stuff about exceptions, but there's some stuff about exceptions that's a little bit weirder. And part of this is the fact that exceptions aren't just used for errors. And this is thanks to what Guido van Rossum called the Harry Potter theory. And I will point out at this juncture, I am not no platforming J.K. Rowling. So there. But what Guido wrote in a blog post, which is, I think, 2005, was I'm sure that when J.K. Rowling wrote the first Harry Potter book, planning it as the first series of 7, she had developed a fairly good idea of what kinds of things might eventually happen in the series. But she didn't have the complete plot lines for the remaining books worked out, nor did she have every deal decided of how magic works. I'm also assuming that as she wrote successive volumes, she occasionally went back, picked out a detail to the story and gave it new significance. In a similar vein, I had never thought of iterators or generators when I came up with Python's for loop, or using percent as a string formatting generator, and as a matter of fact, using def for defining methods and functions was not part of the initial plan, although I like it. So in other words, his point is that he didn't realize how he was going to be using some things in the language when he first added them in. It was over the course of development, they became used for other things. And this is the case with exceptions. So I'm going to show you 4 snippets of code that all raise exceptions. And your challenge is to see if you actually know what the exception is. And I'll explain afterwards, and I'll try to pause for a few seconds, but you're going to need to be quick to get that into chat if you want to put it into chat. So here we go. So here, I'm going to do this. Okay, that raised an exception. In fact, this kind of gives it away because IPython is not handling it too gracefully. In fact, what we've got here is a system exit exception. Okay, and in fact, doing import sys exit 0 is the same thing as doing raise system exit 0. You get exactly the same thing. Okay, so that was the easy one. Now let's look at this one. We've got a list, 1, 2, 3, 4. We iterate over the list. Okay, an exception occurred. Do you know what exception? Give you just a second to think about that. And then I'm going to move on and tell you. Okay, here we go. When you have a for loop in Python that comes to an end of its iteration, you will always get a stop iteration. So yeah, we had a couple of people get it. Bravo. That's what an iterator does to indicate that the iterator is exhausted and the for loop should stop. Now, in some cases, you can also get an index error because some iterables that just have sequence semantics and don't have a special iterator that they create will raise an index error to tell the iterator to raise the stop iteration error. So in some cases with for loops, you can get two. Okay. Now this one, yes, this is a for loop, so it's going to raise stop iteration, but it's also going to raise another exception. And that other exception is well, what? Again, I'll give you a second to do that. Okay, that's a little bit of time. I'm going to go ahead and show this so that we don't get too bogged down. When you're reading a file, the way that the file object tells an iterator that it's done is by raising an EOF error. So again, we had a couple of people who are right on that. Excellent. Now we've got one that may be a little bit different. So now we've got a generator. So I just made a list 1, 2, 3, and this generator is just going to return the numbers in the list one at a time. When it gets to the end, will even print out a little note that it got to the end. And I'm just going to iterate over that generator, the generator object that's created. But I am going to break before I get to the end. In other words, I'm going to do this. So we got 1, we got 2, then we broke, and the loop's done. Okay, so now some of you have been getting these all right. So what was the exception raised this time? Because I promise you an exception was raised, and I'll prove it in a second. Okay, that's about my usual pause. So let me go ahead and what happens is, here is a fuller example. So here I'm going to be doing exactly the same thing, except I'm going to be looking for generator exit right here. Okay, so if I run this, this, when you have a generator object, it will raise a stop iteration if it ends if you exhaust the generator. That is normal. If you don't, the yield is actually sort of blocked right after the last time it yields. So we got 1, we got 2. After we got 2, it blocks right here. And if at that point, basically you go out of scope on the generator object, then that will raise a generator exit, and you can actually deal with that if you want to. So this one is not terribly common, but it does happen. And I'll wait a second. And if I take this out, that's what I wanted to do. If I don't break, this generator exit will not be thrown. So if I do that, see, we do not get anything about the generator exception exit being thrown because we don't exit the generator in kind of midstream. Okay. So to summarize, if we don't finish a generator object, then when generator close is called, and that's what would happen when it goes out of scope, that generator object is going to be destroyed, you get this exception raised. And there might be some cleanup you would want to do in your generator object at that point. Okay. Last one, and this one is, I guess maybe I kind of got it reversed. I'm giving this one away. I've got a class here, and the thing I'm going to do is I made an instance of class foo, and I'm just going to access its dunder stir method, just with dot notation, right? And that works fine. Okay, but if I access instead an attribute that doesn't exist, so here I'm going to access bar. Well, there is no bar in either my class foo or my object foo. There is no bar. Okay, what happens then? Well, Python actually handles this in that when we go to get attribute bar, it will actually raise an attribute error. Okay, and I'm catching it here just to show you that it's been raised right at this point where I'm trying to get bar and it doesn't exist. But then to not short circuit the process, I'm re-raising that error. So we got an attribute error, I'm just raising it again. And when this method, dunder get attribute, raises an attribute error, that immediately gets passed off to dunder get attr, which will then do something. I mean, the expectation is that your class will then maybe calculate it, maybe supply it from some other means. It's a way that you can handle if things are not explicitly part of the object, still returning an attribute that appears to be part of the object. And as you can imagine, this is handy in lots of utility libraries and things like that. So that's what happens here. Or if we do this a lot simpler, here I'm not trapping the attribute error at all in my get attr. I'm just doing it in the, just relying on the machinery to pass it along to dunder get attr, and it works just fine. Don't really need that extra bar there. I have no idea what that's doing there. There we go. Okay. So again, if dunder get attribute doesn't find an attribute name, it raises an attribute error, which calls get attr and allows you to do whatever it is you want to do to handle the fact that that attribute is missing. So what do we got? We have in Python, exceptions can be used as a form of flow control. And This happens when the exception condition is fairly rare, when it's something sort of specific and unusual, and it also makes the code a lot simpler. So you think about for loops, you think about the various other things handling exiting and generator, the various use cases I've shown you. All of those are cases where the code is a lot simpler if we can just kind of use the exception machinery in the background and not worry about writing code to handle that, or not worry about having code that needs to be looked at for that. But some people are going to be a little bit squeamish about using exceptions, particularly if you come from another language. This is going to seem weird. It might seem bad. Some people will worry about exceptions being bad for performance, or does it make your code hard to read, hard to understand, hard to test, all of those things. And I guess you're probably not too surprised. My answer is that those are not the problems that you might think. So first, let's look at the performance one. Are exceptions slower? They are somewhat slower. They're not as expensive as they were, say, in the early days of C, but they are a slower thing. If they are something that does not happen a lot, then the cost is negligible, and the code overall will be more Pythonic, which will probably give you other advantages in performance. So here's what I mean by that. Here I've got a count class, and this count class just counts as many times as you say. It's really simple-minded, and it implements sequence semantics. That is, you get item. So if I say get item square bracket 0, it returns a 0, just like it were a list, which means that it raises an index error. And if I use this in a for loop, what's going to happen is the counter is going to count. Then it's going to get that index error, which is one exception. When it gets that index error, the counter iterator here in this for loop is going to then raise a stop iteration error. So we've got two exceptions in this test. Okay, I'm going to be sure to compile that so we have that ready to go. This is the same thing, except it's done in a while loop, and it will count to 1,000. And notice that we have nothing that will cause an exception. Okay, we set our start and end. We check our length, and we don't go past the length, and we iterate our counters so that we just sort of 1, 2, 3, 4, etc. Okay, so this is so simple. Whereas before we had this class machinery and we're raising exceptions and all of that. So the question is, which one of these is faster? And in this particular case, we're just going to use the built-in time. We're going to do the two of them. So test count tests our object. So I'm going to go ahead and fire that off. And it's going to take it a few seconds. Let's see. We've got a comment that not a fan of it with flow control except for design by contract. Okay. I'm not sure I agree with that, but I'm not sure that I want to die on that hill either, to tell you the truth. So, and then we got the other one. So doing our object with two exceptions took us basically a microsecond, whereas doing the while loop that we had that was so simple actually took more than 2 orders of magnitude in terms of extra time. It was over 100 times longer to do the same thing. The reason for that, by the way, was, let me back up real quick, was the fact that in this example, doing this incrementing meant that a lot of integer objects were created and then discarded. So that's why it was actually slower. The point, however, is that if you follow Pythonic patterns, you're likely to end up with faster code, even if that means dealing with exceptions. So Yeah, that's my argument, and I'm sticking to it. And then in dealing with, exceptions for flow control, confusing, unreadable, somehow bad, it is part of the language. So while I would be maybe cautious about doing a lot of this on my own, exceptions as part of the language is something that is pretty much a standard thing in Python. So understanding and using the ones that are part of the language for flow control, yes, definitely take advantage of those. They will make your code more readable, and in many cases, they will make it probably better performing. Now, creating situations where you're using exceptions for flow control on your own, then you might want to be a bit more careful, because then you get into design issues where you might end up, well, tricking yourself and doing something that you think's a great idea and it turns out not to be. But yes, it's not, in my view at least, a bad thing that Python uses exceptions internally for flow control. It's one of the things that makes Python as powerful and as readable as it is. So yes, we're about the end of the time. And as I said beforehand, in Python, I would argue it really is easier to ask forgiveness than permission. So that, I think, is the end of what I've got. I appreciate everybody joining us today for the conference. And I know that we're going to have questions and things like that coming up in discourse. So, and we've got some giveaways and coupons and various things like that going on. But I do invite people to do that. I think once I shut up, they will switch over to the screen that directs everybody to discourse for questions. So again, thanks everybody. Talk to you later.
Hi guys, how are you? Fine. Welcome. So today in this Lightning Talk, we're talking about Lektor as tool to build your data portfolio. So important that to hold a good portfolio is to show to others this work. So in this talk, we're talking about how to do it using Lektor. Lektor, it's a CMS, so it's a static website written with Python and Node.js. So your focus is how to bring Jupyter Notebook inside the Lektor. For to do it, we will use a plugin, Lektor Jupyter, made by Tom Badwin, but this plugin uses a tool for a Jupyter tool, because Jupyter it's a web applications that you can create and share documents with live code, equations, visualizations, and make a narrative test to explain your resolution for the world, or how steps you use to make your analysis. It's it. So you can clean data transformation and make a modeling, data visualization, and machine learning. So it's a powerful tool for if you are data scientist, or you can start in this world. So if you had a talk or you study about something and can show for the world, you can make your Jupyter notebooks inside your website. So with Lektor, you can make it using a CMS really quickly. So do it. I had here my VS Code. I'm pre-install my virtual env. So and the Lektor and the Lektor plugin. So it's a pip install for install your package inside your environments. So now we can start your application, right? So let's do it. So I'm clean my PowerShell here. So we will start our application using a tool inside the Lektor named Lektor Quick Start. Lektor Quick Start. It's a form to start a based blog for your website. So we can make the project name here, Lektor. Lektor DS. Your name, project path. So you can add, yes, I can, a basic blog. Yes. Here we go. Create a project. So this is the structure at Lektor project. We had models to define how you do your blogs and your blog and your blog post and in the other page. When you make a blog post, your content will be here. So here we can see the first one. The first blog has a hello website, and we had a template with HTML. Okay. So the magic to do here for our blog posts. So our blog posts and in the body, it make it for type markdown. So we will change this for Jupyter, and the source will be our attachment. So we record attachments. So this will make transform our notebooks and page for our website. So here we go. Terminal. So we go to inside our project folder. Is Lektor DS for start or Lektor servers. Okay. When here start running and this link. So here we go to welcome to Lektor DS. Okay, come to the admin. So we change the first. This is the oh no. First we add our notebook here. Okay, make the upload and edit our hello website, and the body will be the notebook that we make a upload. Okay, so here we are. We make our project, our our notebook inside a blog post with our comments that you do and our outputs and the tests, so you can here direct it and your admin this vision and your admin, you can make your handle or to it too, so it's really nice for the end, and redirect for your tweet, so you can show to world your work and your studies, your analysis, how you can make your data constructions for the world. So thank you for watching. Thank you Manny for invitation. So it's it. We can make this project in my GitHub, and is it. I loved this time with you, and enjoy with Lektor and Jupyter. Bye bye.
Hi, everyone. Welcome to this conference, and welcome to my talk. This is all very surreal sort of in terms of what I'm seeing and hearing, or more explicitly, not seeing and not hearing. So in case I was not introduced, in case you don't know who I am, so my name is Reuven Lerner. I'm a Python trainer. When there is no pandemic, I typically travel around the world teaching Python to companies all over. Last year, I taught in the US and Europe and Israel, where I live, and India and China. And this year, I'm teaching from home on all sorts of different technologies, be it WebEx or Zoom, or as we're doing here with Twitch. And as I hope you've heard, I just came out with a new book with Manning, Python Workout. I'm super excited. I just got the first print copies a few days ago, and I'm really excited. And if you like the book too, I'm even more excited. So what am I going to be talking about here? I'm going to be talking about generators, coroutines, and what I call nanoservices. And what we have here are a bunch of different technologies and a bunch of different ideas that I've found over the years that people have a little bit of trouble understanding and sort of putting together, and then knowing sort of when, how, why to do it. So I'm going to be sharing with you a bunch of the ideas that I have. Typically when I teach, I don't actually use slides. Rather, I try to do a lot of live coding. And since I have about an hour in which to do it, and I type kind of quickly, so that's what I'm going to do. I will add, I am going to be in the Discord channel. I mean, I'm currently logged into it now, but I'm going to try to avoid it while I'm actually teaching now. But if people have questions afterwards, I would be super, super happy to answer them. I will also tell you that this, I'm going to be using Jupyter Notebook, as I usually do when I teach. And if you want to see what I'm working on while I'm working on it, so I've got this whole thing set up with a package called Git Auto Push. So basically, Jupyter saves about once a minute, and Git Auto Push will push it to GitHub about once a minute. So I'm actually going to put this in the Discord here. And sorry for like interrupting Naomi and the other folks. So if you want to follow my Jupyter Notebook, it's here. All right, and hold on a second. Up to 2 minutes of delay. Okay, and so if you want to follow it, by the way, it'll be available after the talk as well, but this is in case you want to look through it live during the talk. And again, there will be lots of time for questions afterwards. I would be delighted to talk to you folks and hear new things and learn new things. So let me start off with a bit of a warning, which is this is not a talk about async I/O. And we'll talk a little bit later about how this term coroutines has come to be associated with async I/O. This is about generators and generator functions. And I'm going to start off by talking about the iterator protocol, what that is in Python. I'm going to talk to you about generator functions, what they are, and then we're going to talk a little bit about how they work behind the scenes, how they're different from regular functions and yet the same as regular functions, where we would use them. And then how we would use them, why we would use them, what's the use case for them. And that's going to lead us into not just one-way communication with our generators and our generator functions, but two-way communication, leading us to what are known as coroutines. And then we'll sort of talk about why, where, how you would want to use coroutines, leading up to finally talking about some more advanced and modern functionality, which these coroutines, including things like yield from and even like throw, and what the heck are those doing and why would we want to use them at all? Okay, so let's start off. So the first thing is that when you start programming Python, like probably the first day, the first week, you realize that you can use a for loop to iterate over a whole bunch of different things. So I can say for, one item in ABCDE or ABCD, print one item, and sure enough, it works. Amazing. I can say for one item in 10, 20, 30, and print one item, and that works as well. And at a certain point, you just sort of take it for granted that you can use a for loop on all these different types of objects. And the way that that is working is because there's a protocol that all of these data structures, that strings, that lists, that tuples, that dictionaries, that files, that they all adhere to. And that's the iterator protocol. And basically any object that follows that protocol is considered iterable in Python, right? If you follow this protocol, you are iterable. And what does that protocol mean? Well, it's three things. And first of all, you have to respond to iter. And we'll talk about that in a moment. You have to respond to next. And then, and returning your iterator. And then you have to respond to next, returning the next piece of data. And then when you're done, you raise stop iteration. That's the whole protocol in a nutshell. So any object that does these things is considered iterable. Now, we're not going to go into how you could implement this on a class, but if you're implementing a class and it's a collection of some sort, then it's pretty typical to then add dunder iter, dunder next, so that that class, its instances then are iterable as well. But we can actually create an iterator on our own. That is to say, something that something that is both iterable and an iterator. I'm going to paper over the differences here for a little bit, but that looks and feels like a function. So let's take a look at this. So if I say here, def, my func, I'm going to say return 1, return 2, return 3. This function is not really that useful, as we'll see. All right, so I run this function, my func, and I get back 1, and we're done. Right? And pretty obvious, right? Because the function returned here, we never even got to those lines. In fact, the Python byte compiler removed these final 2 lines, so it's not even the bytecode at all. But what if I do something a little different? What if I say here def, my func, I'm going to say here yield 1, and yield 2, and yield 3. This is a whole different kettle of fish. Because now when I run my func, look what's going to happen. I'm not going to get 1 or 2 or 3 back. Rather, I'm going to get a generator object. What is this generator object? So basically a generator is an iterator. Basically a generator object is something that adheres to this protocol. It's even the thing that we would have gotten back from this iter, meaning it knows how to respond to next. Meaning if we run next on it, the built-in next function, it will run our function up to and including the next yield. So if I say next, well, I'm not going to say g equals my func, because my func is going to return a generator object. Sure enough, if I say, what's the type of g? It's a generator. Good thing I called it g, right? And now if I say next on g, what's going to happen? Well, next says to any iterator in Python, run, give me some data, and then go to sleep. And that's exactly what's going to happen here. Next tells our function here, run up to and including the next yield, return the value to me that you got from that yield, and then go to sleep. So our function is currently between lines 2 and 3, and we'll see that in a little bit. And if I say next of g again, it continues from where it left off. So now it's going to continue running until it hits yield 2, returns 2 to us, and goes to sleep again. Next of g gets us 3, and now it's right after that yield 3. So if I now say next to g, what's it going to do? Well, it has to somehow signal to me that it has reached the end of iterations. And how does it do that? With an exception, stop iteration. So basically, a generator function looks and feels like a function and has all the advantages of a function. And yet, it works like an iterator. So we can stick it inside for loops and other places that iterators are expected. For example, if I were to say here, list of my func. I would get 1, 2, and 3. Why? Because when I call list, it is going to take the thing we got back from calling my func, meaning a generator. It's going to say to it, next, 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 and each and everything it gets back from that generator is then stuck into the list. This is why you can do list of ABCD, because list looks at the iterator for the string, asks it one by one by one for its elements until it reaches stop iteration. Stop iteration means I'm done, and that's where the list stops. So basically, we can stick any sort of code we want into this sort of generator function, knowing that each time we call yield, it's going to return a value to whoever's iterating over it. Typically, it doesn't have to be a for loop, but typically a for loop. Okay, so let me just show you one or two more things with this before we dive in a little deeper. So I'm going to say here print before and print, well, let's do this before 1, and then we'll say here before 2, and then we'll say here print before 3, and then we'll say print after 3. And now if I say, watch this, g equals my func, I'll say next to g. Watch what's going to happen. As I mentioned, it's going to run up to and including the next yield, return that value to g, run up to including. So you can see we have other code in there too, right? And after 3, and then stop iteration, because we hit the end of the function. So the way that we indicate that we've reached the end of the iterations here, the way that the iterator protocol talks about it is raising stop iteration. And if here, when we reach the end of the function, it automatically raises stop iteration. Do not raise stop iteration inside your generator. Either you will get confused or Python will get confused or both. And now the most famous example of generator functions is something that you probably use, that would be the Fibonacci sequence. So I'm going to say here def fib, and I'm going to say first equals 0 and second equals 1. And what is the Fibonacci sequence for those of you who don't know? Basically, we get each time we're going to get 0, then 1, and then each time we get the sum of the previous two numbers. So I'm going to do this. I'm going to say while true, yield first. And then I'm going to say first comma second equals second comma first plus second. Meaning, I'm going to have an infinite loop here. And in the infinite loop, we're going to yield first. Whatever first happens to be, it's going to start off at 0. And after we do that, we're going to take second and assign it to first. And we're going to take first plus second and assign it to second, meaning that we're going to sort of shift everything over to the left by 1. Now, normally, if you were to do this in a function, it would be an infinite loop, right? While long list back, you'll use up all of our memory, use up all of our time, not going to run in any sort of reasonable amount of time, right? But if I say g equals fib here, now I can say next of g, 1, next of g, next of g. It helps to use the right name, yeah? And next of g, and so forth. In fact, I can do something like this. I can say here, for one item in fib. Now, if I just say print one item, we're going to be waiting a really, really long time for this to finish. So I'm going to say this. I'm going to say if one item is greater than, let's say, 1, right, then we'll break. Otherwise, we'll print one item, end equals space, and look at that. We've now generated a very large Fibonacci sequence, right? We probably didn't know it went that high, right? Right? We get really big if we want to. Python doesn't care. That's totally fine. So basically, what we've seen here is that generators have this ability to do, it's two things together. They are lazy evaluated. So I'm not going to get everything all at once. Just when I ask for the next value, it's going to give me the next value. This can be infinite, right? So we've represented here an infinite series or sequence. Obviously would use up our memory, even if your IT department is really generous in how much RAM they're going to put into your computer. Okay, so that's kind of nice. Let's just dive in a little bit into our generators. Like, how can Python tell the difference between a regular function and a generator function? How does Python keep track of this stuff? And then we're going to go in and we're going to see some examples of generator functions, and we're going to talk about the two-way things, which are really the point of this talk. But we have to sort of lead up to all this stuff. If I look at fib here, right, what is the type? Well, actually, I guess I can't do it. I have to say g equals fib. Like, for I in range, let's call it 10, right? I'll say here next of g. We'll just like advantage. So if I say the type of g, of course, is a generator. If I do a dir on g, generator object, and inside the generator object, we have all sorts of dunders, all sorts of magic stuff. And then we have a few attributes that are a little more. We have, for example, GI code. and GI frame, GI running. So if I say here, hey, GI running, the answer is false. Why is it false? Because it went to sleep. And I think it was David Beasley who first introduced me to that. When the yield happens, it goes to sleep. I'll just scroll up here a little bit. Each time we're running next, we're getting this value back. So right now it's not running, right? It's not running because, well, we finished with our nexts. What if I say GI underscore code? That is actually a code object. That is the same sort of compiled code object that exists in a function. And remember that Python is a compiled language. When we define a function, the function is compiled into bytecodes, and those bytecodes are stuck inside of a code object from which we can extract either the bytecodes or all sorts of information that helps Python to understand what we want. For example, if I say GI code var names, these are the local variables that are defined in our function. Sure enough, first and second. So that's the function object that's associated with our generator. But there's also GI frame. That is the stack frame. That represents the current values that are running in the actual function. Remember that there's the function object, which sort of defines what the function does, and the function frame, stack frame, which defines how it's running right now. So if I say GI frame there, GI frame. Right, it's got all sorts of stuff in there. If I do a dir on there, we're going to go too deeply into this, but you can see that the frame object has code, globals, last and line number. What if I say GI frame F line number? It says 5. Well, let's go back up for a moment. If I say fib, question mark, Jupiter, 1, 2, 3, 4, 5. It's waiting here on line 5. Sure enough, Python is keeping track of where it is, where it went to sleep. And what if I say here, GI frame F locals? Look at that. It's a dictionary showing us where we are currently in our generator's execution. So Python is, as I like to say, using Python to implement Python. These generators are using dictionaries, they're using integers, they're using strings, all the stuff we know to keep track of where things are. Okay, so let me just take a cup of tea and then talk more about this. Right, and how does Python tell the difference between a regular function and a generator function? It sees the yield. Once you've got yield in there, it's a generator function. And in fact, if I import dist for disassembly, dist.showcode of, let's call it G, I think I can do it on G, you'll see here that among the various things that there are flags, and the flag here saying generator, that's like what points it to be there. It's a bit flag that's set inside of the function object. So Python sort of knows the moment that you use yield, the compiler then treats it differently. So where are we going to use these? Where are we going to use generator functions? I mean, Fibonacci is lots of fun to play with and everything, but where am I going to do it? And there are a whole bunch of different examples of where we might want to use generator functions. One of them is it's just easier to create certain kinds of iterators. Right, so if I know that I'm going to want to iterate over something in a certain kind of way, I could create a whole class, I could define the dunder iter and dunder next and all that stuff, and then raise stop iteration when I get to the end and on and on. But I can just do it inside the generator function, right? So I could say here, I don't know, let's do this. If I say def, I don't know, let's do enumerate, right? So let's do my enumerate, and so you might know that if I say here for index one item in enumerate of ABCD, I'm going to say here print, and we'll say here index : one item, and we get both the number and the letter. And what's going on is enumerate is with each iteration returning a tuple, a number and the item. So if I want to create my enumerate, and it's not a full-blown version, right? I could say here def my enumerate of what's called data. And then what am I going to do? Well, I can say here something like this. I can say index equals 0 for one item in, well, of course I could use enumerate, right? But it's sort of the point not to do that. For one item in data. And I can say here yield index and one item. I can yield that tuple there, and I can say index plus equal 1. And now basically I could say I could just plop this in where I had enumerate before for index and one item in my enumerate, and sure enough I get the same results. So basically, now I'm not saying you should go off and re-implement enumerate. That's probably not a good use of your time. But you can see how it's way easier. It's pretty easy to create these sorts of iterators. You You could do filters. Here's one that I like to show sometimes. So if I read from a file for one line in open, let's do Etsy password, my favorite punching bag, where I print one line. So we're going to get, of course, one line at a time. And you can ignore the extra new line there. That's because we got a new line for the line and a new line for the print. Fine, we'll ignore that for now. But what if I'm reading from a file that I don't want to get it one line at a time? What if I'm reading from a file where I want to get multiple lines at a time in chunks of various sorts? So what I could do is I could say for one chunk in read n of Etsy password and let's say five lines at a time. And then I'm going to print one chunk. Right? And there are times when you're reading from files where you don't want to get one line at a time, you want to get a bunch of them. Well, this is great, except for one little problem, which is no one's defined read n. It's up to us. And this is a perfect place where we can have a generator, where a generator function will allow us to read from each iteration here, and it can do that calculation. So I could say here, def read n, and we'll take your file name, and we'll call it n. And then what do we want to do? Well, what we're going to want to do is, well, open the file. So with open file name as f. That's good. Good start. And then, do I know how many times I'm going to have to iterate over the file? No. So I'm going to say this. I'm going to say while true. And then I'm going to grab n lines, and I'm going to stick them all together with join. But I'm going to do it because, like, I'm such a big fan with a list comprehension, or even better, a generator expression. So I can say here, output equals empty string join of f read line for I in n. So what am I doing here? I'm going to call read line n times. Each time I'm going to get a string. I'm going to join those strings together and put them in output. What if we've reached the end of the file? If you've reached the end of the file, readline returns an empty string. Meaning, when we really reach the end of the file, then we'll get 5 empty strings or n empty strings, and then we will exit. So I can now say, if output, break out of this loop. Oh, sorry, other way, yield output. If output, yield output, else break. And so now, look at this. Oh, it still didn't like something. What did I do wrong here? What did I do wrong? Oh, it is not iterable. Range n. Duh, thank you. Okay, there we go. So you see now I get 5 of them at a time, or I can get 7 at a time. And so by using a generator here, I was able to put sort of an agent to intercept what's going on between me and those other things there. So you can use generator functions for infinite series. You can use them for filtering. Yeah, like I could say I don't want to see any of the comment lines that start with hash marks, any of that stuff. And you might be saying, okay, this is all kind of nice, but like, couldn't we just do this with objects, right? Like, couldn't we just like, create a class and use methods on a class? And the answer is absolutely. But I think there's some elegance and some beauty here to using the local state of a function, that we don't need to use attributes, self.this, self.that. We could just use a function, which is for many people very natural, and it expresses itself very nicely. Am I saying you must do it this way? No, but there are a lot of people in Python who would want to do that this way. Besides, if you're working on an object, you're writing a method, well, then what? Like, you don't want to get all the data back at once. One of the key parts of dealing with iterators and generators in Python is you don't want to get everything in one fell swoop. You want to get it dripped out to you one little bit at a time, so you don't overwhelm memory, you don't overwhelm the user, you don't overwhelm anything there. Okay, so the thing is, there's also, like, I guess you could say that their state is a little more protected. I mean, obviously you can go in and grab it sort of like I did before with inspecting it, but, it would be fine. So let's do something even a little more exciting, a little more sort of, show off what generators can do. And then we're going to start to turn the problem around and see how to make them bidirectional. So one thing I might want to do is, let's say I want to get weather forecast information, right? And so I actually prepared this a little bit in advance so that I wouldn't have to bore you with looking it up online and everything. But basically, you can get a whole bunch of, there's this, the International Weather Service, I think it is. I'll even show you. It's let me just grab this here. Did I grab that? I'm not sure. Things like the UN's weather. I don't even know exactly what it is, but they had some convenient data, and convenient data is like this is taking a long time to load. Fantastic. Okay, so for world weather information, forget it. Who knows who it is? But it was reliable enough for me to grab the. Oh, of course, there we go. It was loading up. All right, I'm not going to waste your time on waiting for a website to load. because websites are always so reliable and fast. Oh, here we go. World Weather Information Service, World Meteorological Organization. Who are they? I don't know, but they have data, so that's good. So what am I going to do? I am going to, well, first of all, it turns out that they have a list of cities in the world. Pretty useful, huh? And that's the list of cities here, just lists countries and cities, and each city has then a unique numeric code. So since the biggest city near me is Tel Aviv, so I found that, and that's 44 here. Don't worry about like the numbers and everything. So what do I want to do? You can actually get weather forecasts from this World Weather Organization. What are they called? I don't know. Can't ever remember what the organization is. In any event, what I want to do is I want to retrieve forecast information for Tel Aviv. So what am I going to do? I'm going to say here, import requests. And then I can say here, well, I'm going to grab the weather using requests. So, and I'm going to put this here. I'm not going to say the ID. I'm going to say 44N. Okay. And I know it's going to come back in JSON. So I'm going to JSONify it there. And so what's request is going to go out. It's going to retrieve information about Tel Aviv in JSON. It's going to de-JSONify it there. And then I can look at weather. And we see we now have a dictionary of dictionaries with some lists containing the forecast. And if I want, I can say here weather of city of forecast day, because they make it super convenient to get this. And you see I have a list of dictionaries now. Wouldn't it be great if I could just like use a generator and grab those one at a time? Of course it would be. That's the point of my talk, right? So def get forecasts for city ID. And now I can actually put back what was there before, which is city ID in our F string. And then what I can do is I can say for one forecast in weather city forecast day yield one, not firecast. That's a different kind of problem. One forecast. So now that I've defined this generator here, I'm just going to move this down here a little bit. Okay. Now that I've defined this here, what I can do is I can say for one item in get forecast. Actually, I can just say G equals get forecasts. And again, Tel Aviv is 44. And now I can say next on G. And look, the first time it takes a little bit of time to run because that's to download it. But then the subsequent times, because it's stored in a local variable there that I downloaded and de-JSONified, now it's like almost instantaneous. And I can get each of the next day's forecasts until, of course, I get to the end when I get a stop iteration. Why do I get a stop iteration? Because we hit the end of our generator function. So far, the story is as follows. We can write these functions that represent infinite streams of data, that represent sorting or filtering or all sorts of other kinds of stuff. And that's pretty great. But what if I want to change things? What if I want to like change, let's read n. What if I want to read a few times 3 lines in the chunk, and then I want to read 5 lines in a chunk or 7 lines in a chunk? There's no way for me to influence my generator function after it has been called. I'm stuck. Now I could of course call it again and open the file again, or get the weather again, but it's sort of a shame because I've already got that local data there. I've already got that connection, and part of the idea of a generator function is that I set things up once and then I can use them multiple times. So what can I do? Well, here's something super weird and interesting but useful that they put in Python, I think starting in 3.3 a number of years ago. No, it was a little before that. It was in 2 already. No, I'm sorry, 3.3 was yield from. So this has been in for a while, including in Python 2. As if anyone still uses Python 2, right? All right, lots of people do. In any event, watch this. I'm going to say here def mygen. I'm going to say here something like this, x equals 100. And then while true, I'm going to say here print after assigning x before while loop. I'm going to say here print now started at top of while loop. And then I'm going to do something super odd. I'm going to say x equals yield x. Or actually, we're going to say x equals. By the way, this is super cool 3.8 syntax, where if you put inside of an f string, it says x equals this. And then we're going to say this after yield, x equals that. And we'll say x equals x times 2. Okay, and then I'll just do here at bottom of while loop. All right. So none of this is new except for this, which is like totally bizarre and new. So let's take a look. I'm going to say here G equals myGen. Okay, it's a generator, right? Type of G, all is good. Have we actually executed anything so far? No, because we have received the generator object back. And so what do you do with the generator object? You say next on G. And sure enough, Python then runs up to and including the first yield. So it assigns x to be 100. It prints out that sure enough x is 100. After assigning x before while loop, at top of while loop x equals 100. And then it yields back 100. So far, no difference. We are exactly at this point right after the yield x. And indeed, if I were to say now G, let's see, G, I, frame, F, what's it, line number? Line no. And we see that we are on line 7. And sure enough, you see here, line 7, we're there. But here's the thing. Assignment in Python. Assignment is always right side before left side. And so we have received this value back, and Python is now stuck on that right side. What value is it going to use to assign to x here? Whatever we send it. We have suddenly created a bidirectional communication mechanism for our generator. No longer are we just receiving and receiving and receiving. Instead, we are now able to send and receive and send and receive, right? It's better to give than receive, something like that. Anyway, we're both going to be sending and receiving. So what is it waiting for? It's waiting for me to send it something. How am I going to send it something? With send, of course. So whatever value I'm going to put in now, g.send of 222, will replace yield x in the assignment, will be assigned to x, and watch what happens. After yield, x is 222. At the bottom of the while loop, x is 444 because we multiply it by 2. And then we go back up to the top, where at the top of the while loop, x is 444, and then we get it back, right? Because it is yielded. And where is it waiting now? It's waiting on the right side of that assignment. Yield has suddenly become an expression, not just a statement. No longer is it just telling us something, it's waiting to receive something because it's on the right side of this assignment. Now, I must admit, when I first saw this, I was like, wow, that is super cool. So what? It seemed like, as I like to say, a solution looking for a problem. So I can send information to my generator. How can that possibly help me? And I'll tell you that I've struggled for years to come up with use cases. It's in the last year or so that I've started to come up with these ideas of what to do. And I'm not saying no one else has good ideas. People have had good ideas. But I would say it's been rare to see people really use this sort of system here so far. These are known as coroutines. This here is how you would create a coroutine in Python. And indeed, the PEP, I forgot the number, but the PEP that is where they define yield as an expression, indeed talks about creating coroutines. And so we know what subroutines are, right? A subroutine is like a function that I call, it returns, I get its value back, like think of it as a function. A coroutine, though, is a function that exists like at the same time in memory. And so I can call it and get information back, and call and get information back. Well, I'm not really calling it, I'm using send. And so you can think of it as like a little in-memory service. So if a lot of modern internet architecture is based on what we call microservices, right? So I'm going to have lots of different services running on lots of different servers. And oh, I want to do this, I'll call this service. I want to do that, I'll call that service. I think of these coroutines as what I call nanoservices. There's some, I don't know, femtoservices, right? They're super small. They exist in memory. You don't have to go to another computer for them. The protocol is ridiculously simple, and yet we can have them do things for us that don't need to go off to another computer somewhere. Why would we want to do this? Because sometimes we have state, and we don't want to have to restart things from scratch. And it feels more natural sometimes to do this as a generator function, as a coroutine, than it would as a class and as an object. Does that mean that using objects is wrong? Absolutely, positively not, right? There might be only one way to do things in Python, but you have your choice of which one way you want to do it. All right, so how then can I use this? How could I use it to, for example, with my readn? So let's go back here. Let me just find readn. I can just write the darn thing, but here we go. So watch what I'm going to do here. I'm going to change my readN generator function so that we can change the value of n on the fly. And you know what? It's not that hard to do. I'm going to say n equals. Just like that. N equals. So now, if I run it as before, it's actually going to break. It's going to break because none type cannot be interpreted as an integer. What the heck is going wrong here? Well, the regular old for loop does not know how to use send. The regular old for loop is actually just using next. And when you use next, it's like saying send with none. So we might want to protect ourselves a little bit here, in which case I'm going to say here something like this. I'm going to say here, right, sent value equals this. And say if sent value is not none, then we'll say here n equals sent value. Right, this is just a way for me to protect myself so it works with new and old things. So right now, it's going to work just fine. But, I can say here, g equals readN of etc password and 7. So we're going to start off that way. Next to g, we get 7 lines. Oh, by the way, it's really ugly. I'm going to print it so you can see them. Print next to g. Okay, so far so good. And remember that you must start with next. The first time that you're using a generator, even as a coroutine, you got to use next because you have to get something back. But now we can send something to it because it's hanging on the edge, the right side of that yield. So now I can say print g.send of, let's say, 3. I get 3 lines. Print g.send of 8. Now I get 8 lines. And so what I've got now is this in-memory service that I can send data to, in this case an integer, and it'll adjust its output based on what I've sent to it. That's pretty snazzy, I think. Okay, so that's how I can do it with readN. And that actually works pretty well. And I could use it with all sorts of things, right? I could, we're going to get back to the weather example in just a little bit. So these coroutines have existed for a while. And as I said, I haven't seen a lot of people use them. I've seen some people use them. But what really flummoxes a lot of people, and what they really don't understand, is another extension to yield. Not yield as an expression, but yield from. Well, I'll just enter this again. And so let me tell you what most people think about yield from. And by the way, when I say most people, I mean including me until recently. And then, in the last year or two, and then I'll show you how yield from is really supposed to be used. And we'll do a few examples with that, and you'll see how, kind of cool it can be. So, you know what? Before I do yield from, let me just give you like 1 or 2 other examples because I just want to like play with this in there as well. So just give me a second here. Oh, there we go. Just want to grab this from here. Okay. So one of my favorite examples to use in my courses is a Pig Latin translator. If you're not familiar with Pig Latin, it's a child's secret language. It's in my book. It's in a bunch of other places. And so let's say I want to translate a word into Pig Latin. And the rule is basically, Pig Latin, I'll just give you the rules very quickly, right? If the word starts with a vowel, and that's A, E, I, O, or U, then add way. And otherwise, move the first letter to the end, and add AY. So how would I do this? I could say here def Pig Latin of word. If word 0 in AIOU, return word plus way. Otherwise, else, return word of 1 to the end plus word 0 plus AY. Okay, so far so good. Now, I'm not trying to suggest that this is a very difficult, very serious sort of thing that takes up lots of computation. But maybe I want to have this as a generator in my system. So I can actually create this as a generator. I can change it a little bit. I can say here, something like this. I can say, right, S equals, or let's do this. I'll say here, output equals an empty string. And then I'm going to say here, while true, I'm just going to keep this the way it was, and then I'm going to copy it. Do this, and then we'll do that. Just so for everyone following along, it'll be a little bit easier, I think. Right, so now I'm going to say, I'm going to redefine it. Redefine as a coroutine. So what am I going to do here? I'm going to say here, well, s equals, I'll do output equals this. And then I'm going to say while true, because we want to have a loop there, right? And I'm going to say here, output equals yield. Well, let's do this. You know what? Hold on a second. Pig Latin service. Actually, I will do it separately like this. Fine. You know what? Here, hold on a second. So I'm just getting myself a little confused here. Watch this. I can say here, def pig Latin service. And then we can say here, output equals empty string. Yeah, this is going to be much better, much easier to read as well. And we can say output equals yield of pig Latin of output. And then we'll say here, if output is none, then we'll break. Okay, much better. So now if I say g equals the pig Latin service, now it's going to be just like before, right? It's going to say next, so we get back. Oh, sorry. Next of g, what did I do here? I did something wrong. I did something wrong. Pig Latin of output. Oh, duh. All right, let's just do this. Test. We'll start with that. Then that's day. Okay, very good. And now I can say g send of, I don't know, octopus or whatever, and it'll give me back, right, g send of computer. And so I've got this here. So I have this little service running here. Okay, so we once again have a service. Now, let's do a second one, a second coroutine that is a chatbot. Right now, again, this is not the sort of coroutine that we talk about with async IO, although there is a connection I'll talk about in a little bit. So how can I do a chatbot using these sorts of coroutines? Well, I could do something like this. I could say here, def bad service chatbot. Right? And why bad service chatbot? Because you're going to see the answers that we can provide to the user. Right? So we're going to say here, the answers are, you know, I guess I'll use double quotes here, we don't do that. Right, so this is supposed to be a chatbot like for customer service, but you know these chatbots are, they don't actually work or do anything. You know, we will get back to you right away, right? You know, your patience is, is appreciated, and like, you know, we love our customers, right? So you've probably been on hold with such places. So then I can say here, yield, can I help you? All right, and so s equals, let's do output. Let's get that. Then I can say here while true. And I can say here if output is none, then we'll break. Otherwise, we're going to say output equals yield of random choice of answers. So I'm going to ignore, and I guess I need to import random here. So I'm going to completely and utterly ignore what the user has written to me. And I'm just going to use one of my canned answers here. So I'm going to say here g equals, well, I guess g2 equals I can just use g equals a bad service chatbot. And I can say next to g just to queue it up. And I can say g.send of I have a complaint, right? We'll get back to right, g send, I have been waiting for weeks. And it says we'll get back to you right away. Hopefully it'll give me weeks again. Why is it not giving me? All right, I'm not sure exactly what I'm doing wrong here, that it's giving me something different each time, but I'll give this send time. Oh, there we go. Just a fluke. Okay. So you now see we have a few more of these services. We're going to get back to these in just a moment. But I want to first show you this whole yield from business and how people interpret it, and then how we can use and take advantage of it. And then I'll show you like grand finale of how this all fits together. So a lot of people seem to think that yield from is if you have a generator and you want to sort of outsource the iteration to someone else. So I could say here, def mygen, and I'm going to say yield from ABCD. So now what I can do is I can say g equals mygen, and I can say next on g, and next on g, and next on g, and next on g. So what, and then next on g is going to give me an error, or a stop iteration. So what's going on here? And this is like the classic way that people are introduced to yield from. They're told, oh, if you have a generator function, and you actually want to iterate over something else, basically we can translate this code into for one item in ABCD, yield one item. And we'll get exactly the same results. So if this doesn't sit well with you, you're not alone, right? Would Python really introduce new keywords, new functionality, just so that we can avoid a for loop? No, that's not what's going on here. The idea is as follows. What happens if you have a generator function. What happens if you have a regular function? Ignore generators for a moment. What happens if you have a function that gets too big? You break it apart into different pieces. You break it apart into pieces so that you can have some control over it, have some understanding, test it, all that stuff. Like, so it should be readable and maintainable. What happens though if your generator gets to be too big? Well, then you break it apart into different pieces. Oh, but wait a second. Can you really? Because when you send to a generator, how is, like, imagine I have my generator function. I'm sending to that, but then it's outsourced the generation to a sub-generator. How's that communication going to work? Yield from is all about that. Yield from is all about creating a generator that itself works with generators, that calls to sub-generators, and making sure that communication flows transparently, so that when you send a value to your coroutine, to your generator, it goes through to the sub-generator, to that coroutine, and all the way back, and it works beautifully and smoothly. So let me show you an example of how this could actually work. And this is a bit of a contrived example, but I think it demonstrates it pretty well. We now have two different coroutines. We have the Pig Latin translator, right? Pig Latin service. And we also have the bad service chatbot. Both of these are coroutines. Let's assume, I know this is a little silly, let's assume that the people who created the Pig Latin service and the people who created the bad service chatbot have merged their corporations, and they thus have to merge their software as well. This means that we're going to have like a combined switchboard sort of service. And so what we're going to need is for people not to connect directly to the Pig Latin service and not to connect directly to the bad service chatbot. Rather, they're going to connect first to a switchboard and then choose which one they want. And then they'll be connected. This is how it could work. Def switchboard. And I'm going to first say like choice equals yield, send 1 for Pig Latin or 2 for support. Bad support at that, but shh. So what does yield mean? Yield means we're going to get that back. It's going to be returned to us. And then because it's yield as an expression on the right side of the assignment, that whatever the user sends is going to be handed to choice. So I can say here, if choice equals 1, then we're going to yield from the Pig Latin service. Notice I put parentheses on there because I want to use the generator from there. Elif choice equals 2, yield from the bad service chatbot. Else, return. This is amazing. I know it seems super simple, like the code is super simple, but that's thanks to yield from. I can now say G equals a switchboard. And I can say next on G. I get back send 1 for Pig Latin 2 for support. So I'm now going to say G send of 1. Okay, Este, that was the first thing I got. Fine. And now what? Now I can say here G send hello. G send goodbye. And G send, papaya. Good, always a good one for, all right. G send elephant. Very good. What now? What now? Well, what if I send, say, G.send? I think I set it up this way. G send with none. I think it'll exit from there. Oh, it takes one argument. Okay. So if I say none? Stop iteration. It stopped. Right? So basically, that was fine. Now, I also could have done this. Let's do this a little differently here. I think this will actually work. Let's just go through all these once more. I think if I actually send it an empty string, it'll exit. So G send empty string. Index error. Okay, fine. So I wasn't smart enough to do that. Let me see if I can quickly fix that here. Right, so we can say here, right, if not word, return. There we go. Okay, so now if I try it again here, switchboard, All right, now if I do gsend, oh, nothing. Now I think I should be able to say g.send of 2. Nah, okay, so this is why I was live coding, folks. So basically, let me see, what am I missing? I actually set these up in advance. All right, fine. Basically, it should be possible. Oh, int is not subscriptable. Let me see what I'm doing wrong here. Let me try one last time. Always the excitement with live coding. Gsend 1 of that. Oh, goodbye, papaya. And then elephant, fine. And then send that. It should have then returned. Oh, I know, because it exited. That's why. my switchboard exited. Here's what I'm going to do. I'm going to say here while true. Aha! Now we should be better off. Ba, 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 ba. Ba. And now I think I'm going to say G send to. Nah, okay, fine. So I messed up somewhere. Regardless, I can now, if I chose 2 instead, I'm going to do this down here. I do next of G, and I say G send 2, then I can do this, right? G send, I have a complaint, and so forth. They'll, send me something there. So basically what this is allowing me to do is have this sort of communication across my generators. And yield from is the way that I can do that. Because if I didn't have yield from, I would need to have something inside of my switchboard generator grabbing the value and then passing it along, and then getting the result and yielding it. What a pain, what a pain. Let me see if I can actually just like grab this from here. Actually have something that I wrote in advance. Maybe I can fix it that way. And if not, then not. All right, pig Latin. Oh, I see. I should have used different names, right? You know what I'm going to do? I'm actually going to do this. I will call it pig Latin translator, and I will grab the one that I defined before in what I wrote up. It's like that cooking show where you want to have the things defined in advance, right? All right, got that, and then got that. Let's see now if this will work. So G equals, and if not, and I'll try to have it for people afterwards. Board, right? So we say G send of 1. Oh, G, G next. Next G, very good. And then I can say here G dot send of hello. Oh, I just send it a number. G send of 1. Very good. And then G dot send of hello. All right. And then I can say G dot send of empty string. And then I can say G dot send of 2. Oh, okay. Didn't like that. Fine. I'm messed up somewhere. Sorry about that, folks. Regardless, what you see here is we can actually, I see. Fine. Basically, this allows us, where I see all sorts of BBs from Discord, but I don't want to look at it for a moment because I want to try something else just to sort of finalize and then sum things up. So I want to show you one other example, and this is from the weather example that we looked at before, if we want to use a sub-generator, and then we can also play with things even more than that. And that's what we're going to see what throw does as well. So watch this. I'm going to say here, I'm going to say import requests, and then I'm going to say def get forecasts. And I'm going to say while true. All right, city ID equals yield, enter city ID. I'm going to say yield from get 1 city forecast for city ID. So what am I doing here? This is similar to what I did before, but it's lacking the actual forecast part. So this is going to be my main generator, my switchboard, as it were. Get for says it's just going to go around and around and around, saying enter your city ID. When it gets it, then it's going to say yield from get 1 city forecast. Well, that means I have to define get 1 city forecast, right? For city ID. And now I'm going to do exactly what I did before, which is grab the forecast for a particular city. Let's go back here, go back here, go back here, and we're going to yield. So this is our sub-generator here. And what it means is I can now say G equals get forecasts. Now I can say next of G. What's it going to do? Enter city ID. So I can say here G send of 44 again. It's going to go off. It gives me a forecast. I can say next of G, or actually, well, actually, I have to do G send again. Otherwise, it'll get a little. Actually, will it get angry? I don't think it'll get angry. Actually, yeah, it's fine because it doesn't actually care what I'm sending it. But when it's done, then what's going to happen? Watch this. Next to G. And then it's going to say enter city ID. Because what happened? It exited from this generator, went back here to the main generator, and now it's on the right side of a yield from. So it's waiting to get a new value. And so I can ask for a different city. So I can say g.send of, I don't know, 123. I'm hoping that there is indeed a city of that number. Oh, it didn't have anything. G.send of, I don't know, 45. There we go. So basically, by using this, we were able to grab all of the forecasts for city 44, all the forecasts for city 45, and so on and so forth. So you can imagine using this for all sorts of internal operations and things. But wait a second. The way that I designed this here means that I have to run through all the forecasts in a city before I can go back and choose another city. Now, sometimes that might be fine, but I'd like a little more flexibility. What I'd really like to be able to do is say to the coroutine, hey, you know what? I'm done with city 1. I want to get city 2. Well, how can I do that? How can I send a message to it? Because like the messages that I'm sending right now are just like, city numbers and so forth. I guess I could grab a value here on the right side, but there is another way. And the other way is to use exceptions. And I know that it sounds crazy sometimes to use exceptions for this sort of communication, but it doesn't have to be. I think before Naomi, I missed her talking. I'm sorry. I was talking about exceptions. I saw that a little bit in the Discord before I started my talk. So you might have reviewed some of this before, but what you can do is there is a throw method. And the throw method lets you generate or raise an exception inside of a generator. So here's what I'm going to do. I'm going to say here class, right? I'm just going to say here, right, class, choose another city exception. And we'll say pass. And here we're not using exceptions as an error. We're using exceptions as a way to indicate that there's an unusual event, to send a message. I always think of exceptions as, I don't know what it's like in your countries, but very often in Israel, if you're talking to someone face-to-face and their cell phone rings, they're like, wait a second, I'm going to answer my cell phone. They answer the cell phone, and then when they're done with the cell phone, then they go back to talking to the person in front of them. All right, what can you do? In any event, an exception is sort of like that conversation. It's interrupting the conversation so that they can get the cell phone. So what am I going to do here? I've created a new class of exception. So far, not so exciting. But now I'm going to say here for one forecast in weather, and I'm going to say try. Try to yield a forecast. You just try to yield a forecast. Except choose another city exception. Return. What does this mean? It means that I can prematurely exit from these weather forecasts by causing a choose another city exception. How can I do that? With throw. I can say g equals get forecasts. And then I can say g.send of, let's say 44. Oh, wait, sorry. Next first. Next to g. Okay, then I say g send 44. And we know it's going to give me 4 forecasts. That's why it's a forecast. Oh, okay. Anyway, g send 44. Now I'm going to say g.throw of choose another city exception. All right, watch this. We go back to enter city ID. I was able to basically force ourselves out of that sub generator back into the main generator. Pretty snazzy, I think. And so when you start to think about these generators as these sort of nanoservices inside of memory, inside of your computer, I think that you start to see the potential for building your own small protocols. What do you want to use? How do you want to use it? How do you want to use yield from and throw and exceptions to create this whole communication system that can be very rich and doesn't require the overhead of going elsewhere. 1 or 2 last points before I sum up. So I mentioned at the beginning, I mentioned 1 or 2 times other than that as well, that the whole business with coroutines, people now talk about coroutines with async I/O. And so you might be led to believe, well, there's no connection between them. But actually, async I/O, what does it mean? It means that we're not going to use threads. We're not going to use processes. Rather, we're going to have a whole bunch of functions. And each of those functions is going to run for a little while and then go to sleep. So run, go to sleep, run, go to sleep, run, go to sleep. We're just going to sort of iterate over a whole bunch of functions that run for a little bit and go to sleep. What functions in Python know how to go to sleep? Generators. That's why generators were the first way that async I/O was implemented. And then there was this divergence in the way that it's implemented in the keywords. And so now we use special async defs for those. But they are still related to these generator functions. They're not the same thing, but they are still related. And so that's where the sort of use of coroutines for both of these things comes from. Okay, so I hope this was interesting. I hope this was useful. I have certainly had my eyes open in the last year or two, as I said, starting to look into generator functions from a new perspective, using them in these ways, finding ways to sort of take advantage of these sorts of protocols. I am definitely going to be happy to answer questions as best as I can in the Discord forum. I will also invite you, if you want to follow me on Twitter or join my mailing list or read my book. Any or all are welcome. And I hope this was enjoyable, interesting, and useful. And thank you all very, very much for attending. This was fun for me. And I look forward to hearing more from you first in the chat and then online elsewhere as well.
Hi everyone, my name is Mariatta. I am a Python core developer, and today I want to talk to you about GitHub bots and how you can build one for yourself in Python using github library. So what are GitHub bots? GitHub bots are applications that run automations on GitHub using webhooks and APIs. So here's an example of activities in one same pull request, just to illustrate just how much work you can delegate to bots. This is a pull request to the CPython repository. On the left, that's Yuri, who is a Python core developer, and on the right is one of our GitHub bots, Miss Islington. You can see that in just one pull request, how little work that a core developer needs to do. We do the important things. We apply labels, and we review and approve the pull request. Meanwhile, the bot, Miss Islington, is doing so much more work. From saying thanks, it does the git cherry pick, it creates the pull request, it waits for all of the CI to complete and pass, and then in the end, the bot will automatically merge the pull request and then delete the branch. Here's another example of another GitHub bot that I wrote just for myself. I call it Blackout. What this bot does is basically it will run the tool black, which is a Python code formatter. It will run this only on my own pull request. The bot will check the Python codes in my pull request. It will automatically reformat the code and make additional commits and push it to the pull request. So, how does this all work? The bot makes use of webhooks. You can configure in your repository, you can add webhooks to your GitHub repository. Basically, what it does is that GitHub can send you notification of events that are happening inside your repository. There are various events like pull request events or issue events or status related events. There are lots of events. You can read the complete documentation in the developer.github.com/webhooks. So what happens is that when the webhook is sent, GitHub will send a post request to a web service endpoint. And so you need to have a web service to receive that webhook event. The web service can be like something like a Django web server if you want it. It can be a Flask apps, and there are lots of web options for you for writing a web framework in Python. But for the purpose for core Python team, we write this in Python. We build this using AIO HTTP and github library, and we host it in Heroku. So that's one direction where GitHub can send you events, webhook events to your web service. What about the other direction? What if now after you receive the web service, the webhook events, you want to start performing actions on GitHub? Say you want to create a pull request, or you want to create an issue, or you want to close an issue automatically or apply labels. You can do that by calling GitHub APIs. So there are plenty of APIs available. Pretty much almost everything you can do on GitHub through the web UI, you can do through the API. So maybe now you're thinking like this all sounds super complicated, like what even a web service, what is a webhook? Okay, it's really not that complicated, not if you use github library. Github library is an async Python library that's developed specifically for working with GitHub APIs and webhooks. It works on Python 3.6 and up. There is support for working with async web frameworks such as AIO HTTP, Tornado, or HTTPX. So here's an example comparison of making REST API calls to GitHub. On the left is how you would do it using the request library. On the right is the code doing the same thing using github and AIO HTTP library. If you notice on the left, if you use the request library, which you totally can, but the thing is you would need to construct the appropriate request headers that are required by GitHub, and then you can make an API call. Now you can see on the right, some of those details are abstracted out and the code looks simpler and cleaner using github. And additionally, instead of typing out the full GitHub API URL in github, you would simply pass in the actual API endpoint, not the full URL, because github takes care of that internally. Not only that, github is handy for making API calls to GitHub. It has the framework and routings for handling webhook events. github also takes care of verifying webhook secret and payload delivery headers, so you can just focus on writing the actual logic of the webhook handler. So on the right is actually an actual working code example for automatically closing a pull request as soon as it gets opened. Like maybe you have reasons for to do this, maybe you just not accepting any pull request at all, and that's fine. The thing is, it's not complicated. There are 4 lines of code that you write here. The first 2 lines basically says, I'm going to wait for the events, for the pull request open events and the pull request reopened events. The last line where it says gh.patch, that's the one line that's the API call to GitHub to close that pull request. It's 4 lines of code. As you can see, it's not complicated. You will not need to write like thousands of lines of code to write GitHub bots. Now, starting in version 4.1, GitHub provides support for working with GitHub apps. The 2 utility functions are the getJWT. This function will construct the JSON web token that's needed for GitHub app authentication. And the other utility helper for GitHub apps, for working with GitHub apps in GitHub, is called the get installation access token. This is needed for authenticating your API calls to GitHub as a GitHub app installation. And if you're writing GitHub actions, that's also supported by GitHub starting in version 4.0. So, now if you're ready to learn more and excited about building your own GitHub bots, please check out my tutorial. I have written a complete walkthrough that will guide you from start to the end of building a GitHub bot from scratch. This tutorial will take about 3 hours to complete. And if you'd like to learn more about GitHub itself, the documentation is at github.readthedocs.io. So thank you so much for joining me and for listening to my talk. I really hope you enjoy it. I really hope you learn something new. And I hope you get excited in building your own GitHub bot. If you enjoy my talk, or if you appreciate my work in open source, please consider sponsoring me on GitHub. Thank you so much.
Hello and welcome to Python Bytes, where we deliver Python news and headlines directly to your earbuds. This is episode 191, recorded July 14th, 2020. I'm Michael Kennedy.
And I'm Brian Okken.
And welcome, special guest Ines.
Hi.
Yeah, it's great to have you here. So I want to kick this off with a cool IoT thing. Now, IoT and Python, they've got a pretty special place, because when I think about Python, I think of it as not being something, that sort of competes with assembly language and really, really low level type of programming for small devices. But, amazing people put together MicroPython, which is a re-implementation of Python that runs on little tiny devices. And we're talking like $5 microchip type devices, right? Have either of you all played with these?
No.
Yeah. No, I haven't, but like I've been seeing a bit of this from my brother. So he's pretty amazing. Like he's a bit younger than me. He's an event technician, and he recently taught himself programming and everything just so he can build stuff on these like tiny Raspberry Pis. And like I don't know, he's doing super advanced stuff. It's been really interesting to see him learn to program. And he's incredibly good. He has like amazing instincts about programming, even though he's never done it before. But like, so I've been kind of watching this from afar, and it made me really want to build stuff. So I'm very curious.
Yeah, I've done the Circuit Python on some of the Adafruit stuff.
Exactly. So with Ines, I always just want to build these things. I'm like, what could I think of that I could build with these cool little devices? In my world, I don't have it. Maybe if I had a farm, I could like automate, like watering or monitoring the crops, or if I had a factory, but I just don't live in a world that allows me.
I don't know. Do you have pets? Maybe you can build something for pets.
We generally don't have pets, but we are fostering kittens for the summer. So I could put a little device onto one of the kittens potentially. A GPS tracker. Yeah. So in general, you have to get these little devices, right? You've got the US PyCon, we got the Circuit Playground Express, which is that little circular thing. It's got some like 10 LEDs and a bunch of buttons and other really advanced things like motion sensors and temperature and so on. Probably the earliest one of these that was a big hit was the BBC Microbit, where I think every 7th grader in the UK got it. Some grade around that scale got one of these, and it really made a difference in kids seeing themselves as a programmer. And interestingly, especially women were more likely to see programming as something they might be interested in that group where they went through that experience. So I think there's a real value to working with these little devices, but getting a hold of them can be a challenge, right? So you've got to physically get this device. That means you have that idea of, I want to do this thing, and then I have to order it from Adafruit or somewhere else, and then wait for it to come. And my experience has been, I'll go there and I'm like, oh, this is really cool. I want one of these. Oh, wait, no, it's sold out right now. You can order it again in a month. All right. So getting it is a challenge. And also, if you're working in a group of, say, like you want to teach a high school class or a college class or something like that, and you want everyone to have access to these, well, then all of a sudden the fact that maybe it costs $50 wasn't a big deal. But if it's $50 times 20 or 100 kids, then all of a sudden, well, maybe not. So I want to talk about this thing called Device Simulator Express. So this is a plugin or extension or whatever the things that, I think it's extensions, that VS Code calls them, that makes VS Code do more stuff. And it's a open source, free device simulator. So what you can do is you just go to the Visual Studio Code extensions thing and you type device, probably is sufficient, but Device Simulator Express, and it'll let you install this extra thing inside of VS Code that is really quite legit. So it gives you a simulated Circuit Playground Express, a simulated BBC Microbit, and the most impressive to me is the Clue from Adafruit, which actually has a screen that you can put graphics on. So really, really cool way to get these little IoT devices with Circuit Python, so Adafruit's fork of MicroPython on there. What do you guys think? See that picture? Look how cool that is.
Yeah, so you can write Python in one tab and then just have the visualization in the other. That's pretty cool. Yeah.
Yeah, exactly. And it's very similar to, say, what you might do with Xcode and iPhones, where you have an emulator that looks quite a bit like it, or what you would do on the Android equivalent. And I actually think this is a little bit better than the device because it's actually larger, right? Like the devices are really small, but here's like you could be like a huge thing on your 4K monitor with a little Clue device. So you can simulate Circuit Playground Express, BBC Microbit, and the Clue in here. And we just say new project, and it'll actually write the boilerplate code for the main.py or code.py or whatever it's called that the various thing is going to run. And it, like you said, Ines, on one half it's got the code, and the other half it has the device that you can interact with.
I was thinking that a couple cases that would be great is, like you were saying, trying to get a hold of it, but you might not even know if the concept that you're going to use is really going to work for the device you're thinking of. So this would be a good way to try it out, to try out whether the thing you're thinking of trying in for your house or whatever would actually work for this device. The other thing was,
go ahead.
So you brought up education and that it's big. I was thinking about a couple of conferences where they tried to do the display, and sometimes try to have like a camera or something.
Yes.
Sometimes it works and sometimes it doesn't. This way you could just do a tutorial or in a teaching scenario, and everybody could see it because it's just going to be displayed on your monitor. So.
Right, your standard screen sharing would totally work here. That's a good point as well.
Yeah.
And it doesn't have to be all or nothing. Actually, what's really interesting is this thing isn't just an emulator, but you can do debugging. You can set like a breakpoint and like step through it running on the device, simulate it, or you can actually run it. If you had a real device plugged in, you can run it on there as well, and then do debugging and breakpoints and stuff on the actual device.
Yeah, I always admire people who actually use like the proper debugging features. I know VS Code has like so much of this, and I'm always like, I should use this more, but I'm like, okay, print.
print. Yeah, there's some really cool libraries that will actually do that. I can't remember what it's called, but Brian and I recently covered one that would actually like print out a little bit of your code and the variables as they change over time. It was like the height of the print debugging world. It was really, really cool. I wish I could remember. Do you remember, Brian?
No, we actually covered a couple of them. And,
I know.
So,
that's a problem. We cover thousands of things on here. So another thing that's interesting is like, okay, so you see the device, some of them have buttons and they have lights, and you can imagine maybe you could touch the button, but they also have things like temperature, gyrometer type things, or like you moving it or motion sensing, or even like if you shake it. This thing has little ways to simulate all that stuff. So you can like have a temperature slider that freaks it out and says, hey, the temperature is actually this on your temperature sensor, and so on. So all the stuff that the devices simulate are available here.
Oh, that's neat.
Cool.
Yeah. So I actually had the team over on TalkPython not long ago. So people can check that over at talkpython.fm. And yeah, I'm also really excited about what you got coming here next, Brian. What is that?
Yeah. Well, speaking of debugging versus test, we didn't really talk about testing anyway. I'm really excited about.
Talked about testing.
Yeah. So I was thinking that I hardly ever use a debugger for my source code, but I use a debugger all the time when I'm debugging my tests. I don't know. It's just something different about it. But but I've been running a lot of tests and debugging a lot of tests lately because PyTest 6, the candidate release, is out. Now, by the time this episode airs, I don't know if the release candidate will be released or just the release candidate still, but it's you can install it. We'll have instructions in the show notes, but essentially you just have to say 6.0.0 RC1 and you'll get it. But so there's a whole bunch of stuff that I'm really excited about. There's a lot of configuration that you used to be able to put in lots of places in your PyTest ini or your setup config or tox.ini or something. The PyTest 6 will support pyproject.toml now. So if you've jumped on the TOML bandwagon, you can stick your PyTest configuration in there too. There's a lot of people excited about the type annotations. So the 6.0 is going to support type annotations. So it actually was a lot of work. There was a volunteer that went through and added type annotations to a bunch of it, especially the user-facing API. And why this is important is if you're type checking you're running MyPy or something over your source and everything, your project, and why not include your tests? But if PyTest doesn't support types, it doesn't really help you much. So it will now. So that's really, really cool addition.
What this is basically the API of PyTest itself is now annotated with types.
Yes, and a lot of the internal code as well. So they actually went through and did a lot. There was a lot of work, and if you look at the conversation chain, it went on for it was a several month project. So,
wow, what does that mean for compatibility? Does that make PyTest like 3.6 only and above? Do you know?
Well, I think I think the modern versions of PyTest really already are 3.6 and above. I'm not
Right.
sure.
So then the door was open to use that, because otherwise
I mean, it would
would,
be a very weird move to like release a completely new version with Python 2 backwards compatibility. Like that's
Yeah,
like,
why
you
do
wouldn't
that?
do that, right? I mean, it's I think the message it sends is like not great.
I totally agree.
There is a pinned version of PyTest. I don't remember which one it is. That is still supports 2.7 if you're on it, but no new features are going in there. The thing I'm really excited about is a little flag they've added called no header. So don't use this. Most people don't use this. But when you run PyTest, it prints out some stuff like the version of Python, the version of PyTest, all the plugins you're using, a bunch of information about it. All this stuff is really important for logging. If you're capturing the output to save somewhere or do a bug report or something, that information is great to help other people understand it. It's what I don't like about that is that it's not helpful if you're writing tutorials or if you're writing code to put on a slide or something. All that extra stuff just takes up space and it distracts. So if you're doing
or it
things
confuses students. Yeah, like I've had students say, like, I ran it, I think PyTest in PyCharm, and it has like some kind of output just stating where it is and what it's doing. They're like, this didn't work for me. I'm like, well, that was just random output from the tool. You're not actually supposed to try to run that part. You know what I mean? But I mean, I saw why they saw that, but at the same time, like, the ability to just say, like, these details don't matter in the long term is great.
Yeah, so I'm excited about that, to trim it down. There was a plugin called TLDR, too long, didn't read, but it actually didn't take enough of the header off than I wanted. So I had my own tool that would do this, but now I've got this, which is great. And then so a lot of the configuration, there is a chance for human error if you type something wrong and you type a variable name wrong. And so I really like this new flag called strict config, which will throw an error if there's something, if you have the PyTest section of your configuration has something that it doesn't recognize. And it probably is just you misspelled some variable or something.
Yeah, that's good to know.
I can't remember the version, but it was I think it was in PyTest 5. They added some code highlighting stuff that.
Yeah, that's super cool. I discovered that just the other day. I just somehow updated all my dependencies in some environment, and suddenly PyTest output was colored, and I was like, "Whoa, this is amazing!" Yeah.
Yeah, the syntax highlighting, I love it.
Nice.
But there's times where you don't want that, I guess.
Oh yeah, sure, yeah.
So there's a new flag to turn it off. But and then a little tiny detail that I really like is the diff comparisons on PyTest are wonderful. But they didn't do recursive comparisons of data classes and adder classes, but now they do. So that's neat. There's a whole bunch of new features. There's fixes. I ran through some of the features I really liked. There are deprecations, and it's a large list of breaking changes and deprecations. That's why they went to a new number, PyTest 6. But I went through the whole list, and I didn't see anything that was like, oh, that's going to stop me. I'm going to have to change something. But
okay,
yeah,
that's good to know. Like, I mean, if you say, oh, there was nothing that like you were using, I feel confident that maybe there's nothing in my code either.
Yeah, and I knew that somebody was going to ask, is my PyTest book still valid? Yes, it is. But I'm going through it right now. I haven't gone through the whole thing yet to make sure. The side that is not compatible is not the book. The book's fine. It's I have a plugin that now is broken. So PyTest check still works, but if you depend on xfail, PyTest, this is a corner case, but if you depend on PyTest check and the xfail feature of it, it doesn't work right now, so I'll have to fix that.
So you would say xfail fails temporarily?
Yeah. It actually marks everything as a pass. So if you mark xfail.
Oh wow, that's like xfailception. Yeah.
Yeah.
It totally is.
It's really bad. So anyway, I'll have to get back to that.
Yeah, no, this is really exciting that PyTest 6 is out. Super cool. I know that there was some waves, some uncertainty in the ecosystem. So it sounds like that got ironed out. Things are going strong. New versions coming out. I even saw that Guido had tweeted retweeted the announcement and said, "Yay, type annotations coming in PyTest." Of course, he's been all about type annotations these days. We'll come back to that later in the show, actually.
Yeah.
So Ines, I know you work a lot with text, but are you frustrated with it? What's the story of this name here?
Oh, my point of the day.
Yeah, text attack. What is text attack? Tell us about it.
No, I thought I'd present something from my space, obviously.
Yeah,
and
awesome.
there's this new framework that I came across, and it's called Text Attack. Yay. And it's a framework for adversarial attacks and data augmentation for natural language processing. So what are adversarial attacks? You might have actually seen a lot of examples of it. For instance, an image classifier that predicts a cat or some other image, even though you show it complete noise and you somehow trick the model. Or you might have seen people at protests wearing like funny shirts or masks to trick facial recognition technology. So really to trick the model into to like, not recognize them. Or the famous example of Google Translate suddenly hallucinating these crazy Bible texts. If you just put in some complete gibberish, like just ga, 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 and then it would go like, the Lord has spoken to like the people, stuff like that.
That's amazing.
Yeah, I include a link to an article by a researcher who explains like why this happened and shows the example. But it's pretty fascinating. But I think it all comes down to like the fundamental problem of like, how do you understand a model that you train, and what does it mean to understand your model, and how does it behave in situations when it suddenly gets to see something that it doesn't expect at all, like ga ga ga? What does it do? And the thing with neural network models is you can't just look at the weights; they're not linear. They're like you can't just look at what your model is. You have to actually run it. And so that library Text Attack that lets you actually try out different types of attacks from the academic literature and different types of inputs that you can give a model to see whether it produces something that you're like not happy with, or that's like really weird and exposes some problems in your model. And it also lets you then, because normally what's the goal? The goal is, well, you do that and then you find out, oh, damn, like if I suddenly feed it this complete nonsense, or if I feed it Spanish text, it like goes completely in the wrong direction and suddenly predicts stuff that's not there. And if you deployed that model into like a context where it's actually used, that would be pretty terrible. And there are much worse things that can be happening. So you can also create more robust training data by like replacing words with synonyms. You can swap out characters and just see how the model does. So I thought that was very cool. And yeah, in general, I think adversarial attacks, it's a pretty interesting topic. And yeah.
Yeah, it's super interesting. So the idea is basically you've trained up a model on some text, and for what you've given it, it's probably working. But if you give it something you weren't expecting, you want to try that to make sure that it doesn't go insane, at least.
Yeah, exactly. And it can expose very unexpected things, like the Bible text, for example. That sounds really bizarre when you like first hear it. But one explanation for that would be that, well, especially it happens in low resource languages where we don't have much text, and especially not much text translated into other languages. But there's one type of text that has a lot of translations available, and that's the Bible. And so, they're parallel corpora where you have one line in English, one line in Somali, for example. And then people train their models on that. But one thing that also is very specific about Bible text is some Bible text has some words that like really only occur in the Bible text.
Right.
It uses some really weird words. So what your model might be learning here, or could be learning here, is if I come across a super unexpected word that's really, really rare, that must be Bible. And also the objective is you want your model to output a reasonable sentence. So the model's like, well, okay, if that's the rare word, then the next word needs to be something that matches. And then you have like this bizarre sentence from the Bible, even though you typed in ga, ga, ga.
Yeah, how funny.
Yeah.
Yeah, so it looks like they have actually a bunch of trained models already at the Text Attack Model Zoo, they call it, I guess, where you could just grab them and just... Yeah, cute. And so you can just take these and run it against it, like the movie reviews from Rotten Tomatoes or IMDb or the news set or Yelp, and just give it that kind of data and see how it comes out, right?
Exactly, yeah. So I think that's pretty cool. And yeah, and then you can also generate your own data, or to load in your data and generate data that maybe produces a better model, or like covers things that your model previously couldn't handle at all. So that's the data augmentation part. And I think that's that's all very important. And I think it's also very important to understand the models that we train, and really try them out and think about like, what do they do and how are they going to behave in like a real world scenario that we care about.
Right, because as soon as you're making decisions on this data,
yes,
right, on
course.
these models.
Yeah.
I guess soon as a human is convinced that the model works and they start making decisions on it, right, that could go bad if the situation changes or the type of data that comes in.
Especially if the model is bad. Like I'm always saying, like, well, people are always scared of these dystopian futures where like we have AI that can, I don't know anything about us and predict anything and works. But the real dystopia is if we have models that kind of don't work and are really shit, but people believe that they work. That's much more. It's not even about whether they work. It's about whether people believe it, and then that's where it gets really bad. And
yeah, and that's way more likely. Sorry, Brian.
Yeah. Yes.
Go ahead.
It's a more difficult world to test this sort of stuff, to figure out what does it mean for a model to be bad? How do you tell if it's bad? And models can be both working and with some data sets and to just produce gibberish with, or I guess in this case the reverse, not produce gibberish if you pass in gibberish.
Actually, I just realized it ties in very well with the PyTest point earlier, and just like, machine learning is quite special in a way that it's code plus data. Code you can test, you can have a function, and you're like, yay, that comes in. That's what I expect out. Easy, write a test for it. I mean, I know, it's not that easy. Testing is hard, but like fundamentally, yes.
It's somewhat deterministic, at least. Right?
Yeah.
Like.
And even if it's not, there's like something you can, test around it, and it's much harder with the model.
Yeah, for sure. Yeah, how interesting. All right, before we get to the next item, just want to let you know this episode is brought to you all by us. Over at Talk Python Training, we have a bunch of courses. You can check them out. And we're actually featured in the Humble Bundle that's running the Python Humble Bundle right now. So if you go to talkpython.fm/humble2020, you can get $1,400 worth of Python training tools and whatnot for $25. So that's a pretty decent deal. And Brian, you mentioned your book before. Tell people about your book real quick.
Yeah, so Python Testing with PyTest is a book I wrote, and it's still very valid, even though it was written a few years ago. The intent was the 80% of PyTest that you will always need to know for any version of PyTest. And I've had a lot of feedback from people saying a weekend of skimming this makes it so that they understand how to test. So it's a weekend worthwhile. So
yeah, absolutely. And Ines, you want to talk a little bit about Explosion, just to let people know?
Yeah, so I mean, some of you who are listening to this might know me from my work on Spacey, which is an open source library for NLP and Python, which I'm one of the core developers of. And that's all free, open source. And we're actually just working on the nightly version or the pre-release of Spacey 3, which is going to have a lot of exciting features. And I might also mention a few more things later on. And so that's already going to be out by the time this podcast officially comes out. Maybe not. I don't want to overpromise, but you can definitely try that out. And we also recently released a new version of our annotation tool, Prodigy, which comes with a lot of new features for annotating relations, audio, video. And the idea here is, well, once you get serious about training your own models, you usually want to create your own data sets for your very specific problems that solve your problems. And often the first idea you have might not be the best one. It's a continuous process. You want to develop your data. And Prodigy was really designed as a developer tool that lets you create your own data sets with a web app, a Python backend. You can script. So that's our commercial tool. That's how we make money. And it's very cool to see a growing community around this. So that's what we're doing. we have
Yeah,
some more cool
awesome.
stuff planned for the future. So stay tuned.
Yeah, people should check it out. Actually, you and I talked on Talk Python 202
Yes.
about building a software business and entrepreneurship. You had a bunch of great advice, so
Yeah.
people might want to check that out as
Did you,
well.
did you actually know these episode numbers by heart, or did you look that up before?
Some of them I know, but that one I used the search.
Okay.
I remember you were on there. I remember what it was about, but not the number.
I just put together that I know 2 people from Explosion, so that's interesting.
Yeah, and
Yeah,
Sebastian.
absolutely.
Sebastian.
Probably. Yeah,
Yeah.
he was on your podcast recently, which
Yes.
I feel really bad. I need to listen to. I wanted to listen to this because he advertised it with like it will tell the true story behind his mustache, which I
Yes.
really wanted to know. But then I was like, oh, I'll need to listen to this on the weekend, and I forgot. So yeah. If he's listening, I'm sorry. I will definitely. I need to know this, so I will listen.
Excellent.
So
Yeah, he's
don't
doing cool
spoil
work.
it.
Doing great work on Fast API. All right. Speaking of people that have been on all the podcasts as well as Brett Cannon, he recently wrote an interesting article called "What is the Core of the Python Programming Language?" And he's legitimately asking, as a core developer, what is not the maybe lowest level, but what is the essence, I guess, is maybe the way to think about it.
Oh wow! I only
So-
just got the core pun. Like it did not occur to me when I first read the article. I'm really I feel really embarrassed now.
Same here.
To be fair, English is
Yeah.
not my first language, but still, it's not about that.
Yeah.
Anyway,
I
sorry for
first read it, I was thinking like, okay, we're going to talk about what is the lowest level, and yeah, okay, it's probably C and CVal.h, CVal.c, and so on. But really, the thing is, Brett has been thinking a lot about WebAssembly, and what does that mean for Python in the broad sense. He and I talked about it on Talk Python. I think at the very last PyCon event, we did a live conversation there about that. And it's important because there's a few areas where Python is not the first choice, maybe not the second choice, sometimes not even the 10th choice of what you might use to program some very important things like maybe mobile, maybe the web, the front end part of the web, I mean. So there's a few really important parts of technology where Python doesn't have much reach, but all of those areas support WebAssembly these days, right? And if you have something in C, you can compile it to WebAssembly. So there's some thought about like, well, what could we do potentially to make a WebAssembly runtime for Python so that Python magically almost instantly gets access to what was just JavaScript front-end frameworks space, what is mobile, iOS and Android, and all those things allow you to directly run JavaScript as part of your app. So how would we make that happen? So it's pretty important, right? If we could solve that problem, like Python is already so popular and its growth is so incredible. Like what if we could say, oh yeah, and now it's an important language on mobile and it's an important front-end language framework. Like that would just take it to the next level, or maybe a couple levels up if you do them both. And WebAssembly seems to be one of the keys to kind of bridge that gap, right? So Brett talks about in this article how for so long we've just had CPython is what we think of when we have Python. Sometimes people use PyPy as a partially JIT compiled version, sometimes faster version of Python, but not always, because the way it interacts maybe with C, libraries that you might be using through packages and so on. And really it's a lot of Python's dynamic nature makes it hard to do outside of an interpreter, where, to be clear, WebAssembly is a compiled language, right? So if you're going to put it over there, maybe it's going to require it to be compiled. So this is a really interesting thing to go through and read and think about with Brett. He talks about things like, well, how much of the Python language would you have to implement and still consider it to be valid Python? Like we talked about MicroPython, and usually people they don't look at that and go, that's not Python, that's fake, right? No, like it's Python, but it's not as much Python, right? You don't have all the APIs on MicroPython as you do on regular Python. So questions like, do you still need a REPL? Could you live without locals, right? The ability to ask what the local variables are and so on. So he said he didn't really have a great great answer. It's more of a philosophical, like we need to solve this. But I do want to share some of my thoughts on this. And I feel like maybe what we could do is we could come up with like a standard Python language definition that is a subset of full Python, right? Here's the essence. Like, okay, we have to be able to create classes. We have to be able to create functions. You have to define strings. Probably you want type annotations. But do you need a val? Maybe, maybe not, right? So like that, if you could have a subset of the language that was smaller, as well as the standard library, because do you really need to like parse CSS hex colors everywhere? Probably not. It's a very underused part of the library, but it's in there, right? So if we could narrow it down, maybe it would be easier to think about how does it go to WebAssembly? How does it go to like some kind of JavaScript runtime or something like that? And if it sounds crazy, you know, the .NET people did this. They have a .NET standard class library language. They got it running on WebAssembly. So there's an example of it out there and something that's kind of sort of similar, right? So I think this would just open stuff up if you could get Python in these places. What do you guys think?
I mean, I was never so sold on WebAssembly and especially WebAssembly and Python until I watched Dave Beasley live code a compiler at PyCon India, I think it was, and I was like, oh, this is kind of fun, and I mean, it was just also fun to watch Dave Beasley live code a compiler. But
yeah, for sure.
Classic. But so that did get me thinking. I do think. One question I think we should ask ourselves is like, well, do we really need Python to do all of the things in the browser? Like, does this really have a benefit that like actually makes a difference? A, B, there are a lot of things people use Python for that just wouldn't work in that way. And that's also, I think, part of what makes Python so popular in the first place. Like, for instance, you know, all the interactive computing environments. That's why people want to use Python for data science, IPython, Jupyter notebooks, that sort of stuff. That's why, you know, Python as a dynamic language made so much sense to people, and that's what made it popular. And large-scale processing, like a lot of the type of stuff we're working on, it's like, there's stuff that you can run in the browser, but it's never going to be viable to run large-scale information extraction in a browser because you want to run that on a machine for like a few hours. But I think there are a lot of opportunities also in the machine learning space for privacy-preserving technologies that already exist. I think, from what I understand, Mozilla is working on some features built into the browser where, you know, you can have models predicting things without it being sent to someone's server. And I think that's obviously
an interesting idea, right? Yeah, because if you could have a little bit of machine learning, but you don't have to give up the data privacy aspect of it, that's pretty cool.
Yeah, so I think for that, there's a lot of potential here for running Python in a browser.
Yeah.
Well, we start getting used to saying what is Python is what is the CPython implementation, and we got to remember CPython is the reference implementation for the language spec, and I guess we're kind of getting at maybe we need to split it up and have a core language spec and an extended one or something. I don't know. But the where would you divide the line? Because we've seen, like you said, we've seen things like CircuitPython and other things, and we've actually talked about several smaller languages based on Python that just try to be the same syntax. But at which point is it? When is it? It's not Python anymore. And there's at least some of the stuff. Like I could totally see having a distribution of Python that doesn't have a REPL still count. And I could totally see not having idle, for instance. If something doesn't ship with idle, is it still Python? I think so. And because of idle, then you need tkinter or you need tk stuff in there, and there's a lot of stuff that maybe I would be in, like, could you live without locals? Most of the time, probably. And so I actually think this would be since the web and since mobile is such a big part of our lives, and it will be for a while, this might be a decent dividing line to say whether or not it's for WebAssembly or not. Maybe we should split the division at whatever we need to implement a WebAssembly version of Python. And anything above that line is an extended version of Python or something.
Yeah.
I don't know.
Yeah, that's a good point. All right, I don't want to go too long at this section because I want to make sure we get the others. But I do want to leave you with just some thoughts. What if shipping Python was just shipping a single binary and a thing that ran it? You could do that with WebAssembly. Maybe 2 WebAssemblies, the runtime plus the code. What if all the browsers had capability to plug in alternate runtimes through WebAssembly? So right now you have a JavaScript engine, but what if, like, say, Firefox in Edge and whatnot came up with a way to say, here's a WebAssembly API to plug in alternate runtimes, Python, Ruby, .NET, Java, you name it, and then shipped with the latest version of each of those runtimes. So you just don't have to like, the big problem now is you can do it, but you've still got to download like 10 megs per page, which is not a good idea. So anyway, I think there's a ton of interesting things that open up if this were possible. So I'm glad Brett's still on this, and hopefully he keeps thinking about it. Brian, I still need to learn Pathlib. Do you got any ideas on how I do that?
Really? You're not using Pathlib?
I am I'm just stuck in the os.path world. I just really need to get with the times. Help me out here.
Okay. So Pathlib
I know there's value.
You're like
I just got to get there.
Animal, like os.path.
I know.
No, I
so
mean,
I'm no offense to os.path, but
No, I really love Pathlib a lot, and but there's I gotta tell you that the documentation for Pathlib doesn't cut it as an introduction. You can find what you're looking for, but if you know what you're looking for. But I agree with Chris May. So Chris May wrote a post called "Getting Started with Pathlib." I guess it's kind of he's got a little PDF field guide that you can download, but he has a little bit of a blog post introducing it. But I downloaded it. It's like 9 or 10 pages, and it's actually a really good introduction to Pathlib. So I really like it. The big thing with OS Path versus Pathlib is Pathlib creates path objects. So there's a class that represents a path that you have methods on, and it makes it different for when you're dealing with this. With os.path, it's just strings. So it's manipulating strings that represent paths. So the object's different. I like it. Actually, I switched just for the ability to add build up paths with just having the slash operator. So
yeah, it's really interesting how they've overridden division.
Yeah.
But I think it's a good example of where this makes sense. It's a reasonable use case. It looks good. It's defensible. There are other cases where you're like, oh, did you really have to like overload these operators? But they're fine. I think that's very valid.
Yeah.
Yeah, I agree.
And things like how do you find parts of a path? That when you have to parse paths, that's where Pathlib really shines for me. So if you want to find the parent of something or the parent of the second level parent, there's ways to do that in Pathlib, and in os.path, you're stuck with like trying to split things and stuff, and it's gross. I mean, there are operations to do it, but it's very good to have this relative. I don't know, just all these operators like parent, and then one of the things that took me a while to figure out was I was used to trying to find the absolute path of something. And in Pathlib, finding the absolute path is the resolve method. So if you say resolve and it finds the absolute path for you, you can find the current working directory. You can go up and down folders. You can use globs. You can find parts of path names and stuff. And it's just a really comfortable thing. So this, I think you should give it a whirl. And it's not like it's going to change your life a lot, but the next time you come up with, the next time you're programming, you're like, okay, I got to have a base directory and some other directory. Oh, well, I'll reach for Pathlib instead of os.path. So
yeah, I guess it has been there since 3.4, so I should get with the times.
Yeah, so I mean, now before I could see the objection of like, oh, you have to backport it. And also, I think what I like as well is a lot of integrations that, like, automatically can perform checks whether a path exists, stuff like that. Or for me as a library author, you're writing stuff for users and you want to give them feedback. And for instance, in a library like Click or Typer, which is the modern type hint version CLI interface, which was also built by my colleague Sebastian, you can just say, hey, this argument is a path. What you get back from the command line is a path. It will check that the path exists via pathlib. So it does a whole bunch of magic there.
Yeah, that is super cool.
Yeah, or you can say it can't be a directory, and then you write your CLI, user passes in an invalid path, and you don't even have to do any error handling. It will automatically, before it even runs your code, say, nope, that argument is bad.
Okay, so that's cool. Awesome.
And you don't have to care about Unix versus Mac or PC or something like that.
Yeah, Windows, no offense to Windows, but it's always handling paths, and Windows is always the classic story, also as a library author, where you just probably supporting all operating systems, but Windows just does it a bit differently, and you cannot assume that a slash means a slash.
Yeah, for sure.
Yeah.
All right, well, the final item is yours, Ines, and it's definitely interesting. So if you're working in the machine learning and data science side of things, it might not be enough to just back up your algorithms in your code, right?
Yeah, you also have machine learning is code and data. So this is something we discovered a while ago, and that we're now using internally. So we currently, as I mentioned before, we're working on version 3 of Spacey, and one of the big features is going to be a completely new optimized way for training your custom models, managing the whole end-to-end workflows from pre-processing to training to packaging, and also making the experiments more reproducible. You want to train a cool model and then send it over to your colleague, and your colleague should be able to run the same thing and get the same results. Sounds really basic, but it's pretty hard in general in machine learning. So our Spacey stuff will also integrate with a tool called DVC, which is short for data version control, and which we've started using internally for our models. And DVC is basically an open source tool for version control, specifically for machine learning and for data. So, you can check your code into a Git repo as you're working on it, but you can't just check your data sets and models and artifacts into Git or your model weights. So it's very, very difficult normally to keep track of changes and your files. Most people just end up with this directory of files somewhere, and it can be very frustrating. And so you could think of DVC as Git for data, and the command line usage is actually pretty similar. So you type Git in it and DVC in it to initialize it, and then you can do DVC add to start tracking your assets and add them. So it's I think if you're familiar with Git as abstract it can be at times, you will also kind of find it easy to get into DVC. And it basically lets you track any assets like data sets, models, whatever, by adding meta files to your repository. So you always have the checksum in there, and you always have these checkpoints of the asset, even though you're not actually checking that file into your repo. So, and that means you can always go back, fetch whatever it was from your cache, and rerun your experiments. And it also builds this really cool dependency graph. So you can really have these complex pipelines with different steps. And then you only have to rerun one step if some of the inputs to it have changed. So, in machine learning, you'd often have a pipeline, you download your data, then you pre-process it, then you convert it to something, then you train, then you run an evaluation step, and everything sort of depends on each other, and that can make things really hard. And you never know. You usually have to run everything very clean from scratch, because if something changes, your whole results change. So if you set up your pipelines with DVC, it can actually decide whether something needs to be rerun, or it can also know what needs to be rerun to reproduce exactly what you're trying to do. So that's
that could save you a ton of time and money if you're doing it in the cloud.
Yes. Exactly. Yeah. And you can share it with other people. It's I think it definitely solves a problem that's very real. And the people who making DVC, they've also recently released a new tool that I have not personally checked out yet, but it looks very interesting. It's called CML, which is short for Continuous Machine Learning. And that's really more of the CI, which kind of is logically the next step, right? You manage everything in your repo, and then you obviously want to run automated tests and continuous integration. So the previous looked really cool. Like it showed kind of a GitHub action where you can submit a PR with like some changes to your code and your data. And then you have the bot commenting on it, and it shows like accuracy results and a little graph and how stuff changes. So it's really like these code coverage bots that you've probably seen, where like you change some lines and then it tells you, oh, coverage has gone up or down, and here's the new view of your code. So that's what it looks like. So I think
that sounds
I'm
really
pretty excited
cool.
about this, and it solves a problem. It's already been solving a problem for us, and yeah.
So how does it store the large files? I know it has this cache. Is that a thing that you host? Does it have a hosted thing that's kind of like GitHub, or where's the?
I'm not sure if you probably connected to some cloud, but like normally you have that locally. It also has a cool thing where you can actually download files via the tool. And then depending on where you're fetching it from, if it's a Google storage bucket or an S3 bucket or something, you can actually also tell if the file has changed and whether it needs to be re-downloaded. And so, for example, internally, what we're doing is we're mounting a Google Cloud Storage bucket, or however they call it, locally as like, so it's like kind of a drive you have access to locally, and then you can just sort of type GS, blah, 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 and then the path, and really work with it like a local file system. And that's pretty nice. So you can, you can work with private assets, because the thing is, a lot of toy examples assume that, you just download a public data set and then you train your model and then you upload it somewhere. But that's not very realistic, because most of the time the data you have can't just go in the cloud publicly. So, cool. But yeah, I don't know exactly how it works in detail, but like it can basically fetch, I think from the headers or something, it can tell whether the file you're downloading has changed and whether there's something new.
So with a normal version control, one of the reasons we use it is to try to find what's different. Can you do you do diffs on data, or?
I don't know. Maybe. I mean, I'm not sure if there's. I think the main diff is more like around the results that you get, because diffing large data set, diffing weights you kind of can't. That's really where we're at the other problem, where like you need to run the model to find out what it does, and then you diffing accuracies rather than weights. But I don't know if it does like actual diffing of the data sets, but often the thing that changes is really the models. Like you have you have your raw data, and then you change things about your code. And something changes, and you want to keep track of what it is or how it manifests. So
it's really cool to see them working on this. It's nice.
Yeah. So and also we'll be in Spacey 3. We'll hopefully have a pretty neat integration where, if you want, it's not like mandatory, but if you say, hey, that's cool, that's how I want to manage my assets, you can just run that in a Spacey project, and then it just automatically tracks everything, and it, you can check that into Git and share it, and other people can download it. So that's, I'm pretty excited about that, and it works pretty well. Yeah.
Everything you can do to make it a little easier to work with Spacey and just make it reproducible.
Yeah, and it's just the things are hard. Like I'm not a fan of these. One click, everything just magically works. Like it looks nice and it's a nice demo, but like once you actually get down to like the real work, like things need to be a bit modular. Things need to be customizable. Otherwise, you're always hitting edge cases, or you have these leaky abstractions. I think things should be easy to use, but you can't just magically cover everything by just providing one button. That's just not going to work.
Yeah, because when it doesn't work, it's not good anymore.
Yeah, exactly.
All right. All right. Well, that's our 6 items that we go in depth into. But at the end, we always just throw out a couple of really quick things that maybe we didn't have time to fit into the main section. And I want to talk about 2 things that are pretty exciting. One is, if you care about podcasts as a catalog of a whole bunch of things, I don't know how many podcasts there are. There's probably over 1 million podcasts these days. One of our listeners, Anton Zianov, wrote a cool Python package that will let you search the iTunes directory and query it. It's basically a Python API into iTunes podcasting directory. some people think that that you've got to be part of the Apple ecosystem to care about iTunes, but really that's just the biggest like directory, kind of Yahoo circa 1995 style of listing of podcasts. So if you care about, digging in and researching podcasts, check that out. That's pretty cool. And then I've also, I'm such a big fan of F-strings. How about you two?
Yes.
Yes,
Finally.
right? That was such a great sticker.
I'm finally working in like Python 3 only. I remember, I think last time I was on the podcast, I was saying how like, all these modern things, they're so nice. I wish I could use them more, but we're still supporting Python 2. But like, no, everything I write now, 3.6, yes.
They're lovely, right? And I've talked previously about a tool called Flint, F-L-Y-N-T, which lets you run against an old code base and convert all the various Python 2 and 3 styles of formatting magically into Python 3, which is really nice.
The episode I was.
Yeah, you might have been, right? You're like, I wish I could run this, right?
Yeah.
And I ran that against like 20,000 lines of Python. I found like just a couple errors, reported them, they got fixed. So that's nice. But the thing that's bugged me endlessly about F-strings is I'll be halfway through writing the string and I'm like, oh yeah, I want to put data here. So I got to go back to the front of the string, not necessarily back to the front of the line, but maybe back to like the string is being passed to a function. So I go back to the first quote, put the F, go back forward, and then start typing out the thing I actually wanted, right? Or maybe I'll F-string something when I'm not going to put data, right? So it's like you're halfway through and you want it to become an F-string. Well, PyCharm is coming with a new feature where if you start writing a regular string and pretend like it's an F-string, it'll automatically upgrade it to F-strings.
Yes,
like halfway
thank
through.
you.
Yes, without leaving. So you just say curly variable. It's like, oh, okay, that means that's F-string, and the F appears at the front. It's like, yes. So that is pretty awesome. Anyway, those are my two quick items. Ines, I'm also excited about the one you got here. This is awesome.
Yeah, I had one, which is something coming to 3.9 or in 3.9, which is PEP 585, and which means you can use, when you use type annotations, you can now use the built-in types like list and dict as generic types. So that means no more from typing import list with a capital L.
Yes. Yeah.
Yes. So you just literally, I mean, when I first saw it, I'm like, that looks strange, but like, yes. Yeah. I'm so excited about this. It'll probably be years until I can just like use it all across my code bases because
True.
Yeah, but like, yay.
That's in 3.9?
Yeah.
Yeah, that's in 3.9.
I'm already using 3.9 and I didn't know
then
this.
you can do this.
Oh,
Yeah.
And Guido is one of the guys on the PEP making this happen. Like I said, he's really into typing.
That's great.
So this is really cool because it was super annoying to say, oh, you have this new import just because you want to use type annotations on a collection. Right now you don't have to. And there's actually a bunch of the collection stuffs and iterators and whatnot, like the collections module, like that. A bunch of stuff in there is really nice. And they're compatible, like lowercase list of str is the same as capital list of str, I believe. All right, Brian, what you got?
Oh, I just wanted to I'll drop a link in the show notes. Test and Code 120 is where I interviewed Sebastian Ramirez from Explosion also, and talking about Fast API and Typer because I'm kind of in love with both of those. They're really cool. So, yeah,
absolutely. All right, well, that's a cool one. Definitely going to check that out.
And you find out why he has the cool mustache. So.
Yeah, that's right. All right, so we always end the show with a joke, and I thought we could do 2 jokes today. So I think, Ines, do you want to talk about this first one?
Oh, yeah. I mean, I'm not even sure it counts as a joke per se.
No,
but
it's
like,
more
it
of a humorous situation, I guess, right? Or commentary.
And it ties in. It's Sebastian again. Like he had this very viral tweet the other day where he posted about some experience. I could just read it out because I think it needs to kind of stand on its own. So he writes, I saw a job post the other day. It required 4+ years of experience in Fast API. I couldn't apply as I only have 1.5+ years of experience since I created that thing. And then he says, maybe it's time to reevaluate that years of experience equals skill level. And this was, I was like, it resonated with people so much. I was actually surprised to see like everyone was like, oh yeah, HR, like apparently this seems to be this huge issue, obviously, that like, well, not most job ads are not written by the people who actually work with the technologies, and where you have,
Actually, yeah, this is awesome. And this tweet actually just got covered on DTNS, the Daily Tech News Show, I guess it is.
Oh.
Alongside another posting that said you needed 8 years of Kubernetes experience for another job. But of course, Kubernetes has only been around for 4 years. Yeah, when you say this went viral, it had 46,000 retweets and 174,000 likes. That's got some traction. I feel like this might be a problem in the industry.
Yeah, I was surprised that like so many people are like, yeah, that's a big deal. And it's like, and I mean, it is true. Like kind of the tech hiring sort of seems to be broken, and it's a bit different in my case, I guess. But like I don't qualify for most roles using the tech that I write, and in some cases that's justified because I'm not a data scientist. Just because I write developer tools for data scientists doesn't mean I can do the job. But in other cases, I'm like, there's kind of a ridiculous amount of arbitrary stuff you're asking for in this job ad. Maybe that's needed, maybe not, but like it centers around like a piece of software that I happen to have written, and I do not qualify for your job ad at all. Like,
that's insane.
The last time I wrote a job description, I intentionally left off the college or a degree requirement because all of the other requirements I was listing in there, either they had it from college plus experience or they had it just from experience. So I was fine with that. By the time it actually went live, somebody in HR had added a college degree requirement to it. I just couldn't get away with not listing that, I guess.
Yeah, master's degree in Spacies preferred.
Yeah, I guess another problem there is like, well, look, if HR writes these job ads with these bullshit requirements, then well, who applies? Like, it's either people who are like, yeah, whatever, or people who are full of shit. And then that's the sort of culture you're fostering. And it might not even be the engineer's fault who wrote a very honest job description, but like, yep, who applies to that? Like,
you're going to make me lie about my fast API experience.
Yeah, or people just apply to anything. I'm like, yep, I have 10 years experience in everything. Great. And they're like, perfect. That's what we're looking for. You're hired. And then you wonder, like, why is our company culture so terrible?
I actually did have somebody apply to a job and say they have multiple years of experience in any new language coming up.
Nice. All right, guys. Well, it looks like we're just about out of time. Let me give you one more joke for it. Brian, will you describe this picture and then I'll read what it says?
There's a poorly drawn horse, I think, zebra horse that has white on the back end and black on the front end.
And the text says, I defragged my zebra. I don't even know if people defrag drives anymore. So this is only going to resonate with the folks that have been around for a while.
I saw that there was this great video I came across on YouTube where you can actually watch like a live defrag session, like, I don't know, Windows 95. And it like, I don't know, it takes a few hours and, you can kind of bring back that nostalgia and just put it on your TV and just sit there and like,
Oh, it's like the aquarium you would put on your TV. Beautiful. Like, but for tech. All right. Well, Lucas Manning says, wrapping up. All right. Thank you.
Thanks.
Hello out there in coronavirus land. I'm coming to you from Pittsburgh, Pennsylvania, and I hope you all are doing as well as can be expected in these interesting times. This lightning talk is called Rust is for You. My name is Carol Nichols or Goulding. I am on Twitter and GitHub at Carol's10cents. And I'm here today to talk to you about Rust. We are going to talk about what Rust is, and we're going to compare it to Python. And then I will tell you why I think you should learn Rust. But first, who am I? I am the co-author of the Rust programming language book. I am the co-author of the Rust in Motion video series available from Manning. And I co-founded the world's first Rust consultancy, Integer 32. Before all that Rust programming, I was a Ruby developer. So I have similar experiences as you do in the Python world. And now we're going to get into what Rust is and why I think it's interesting. Rust is a new programming language, newish. It hit 1.0 in 2015, so it has had stability guarantees for about 5 years. It came out of Mozilla research, and Mozilla is interested in using it to slowly rewrite Firefox to be safer and more concurrent. And many other companies have found it to be useful as well. Usually when you look at this runtime speed, the memory safety, and the ease of writing concurrent code, you have to pick one or two of those. With Rust, you get all three, and I'll go into a little bit more detail on these. Rust is aiming to be an alternative to C and C++, but just as fast as those languages are, targeting kind of the same niches, and solving a lot of the memory safety problems that those languages have, as far as null pointer dereferences, buffer overreads, use after freeze, double freeze, seg faults, all of those problems that lead to crashes and security vulnerabilities in the software that we use today. Rust is aiming to fix all of that. So directly, how does it compare to Python? Both Ruby and Python, I would say, are highly expressive. You can write very high level concepts and say very human-like ideas in your code. But to do that, you give up a lot of control as far as where the memory is being allocated and cleaned up and what exactly is going on behind the scenes. If we look at C in this lens, you get a lot of control in C with your memory being allocated and freed, and exactly how you are going about taking each action. But there's very few high-level ideas available to you in your C programs. You have to write, you get the control, but you have to use that control and build up a lot of abstractions by hand. Rust, I feel like, gives you the same amount of control as you would get in C or C++ as far as memory management, and gives you some more expressiveness. Now notice it doesn't go quite up as high as Ruby and Python does, but Rust does have a lot of high-level concepts that compile down to code that is as fast as the code you would write by hand in C. You get iterators and traits that are like protocols, and you get to express a lot of ideas, high-level ideas, while still getting that low-level control. So let's look at some details here. Python is interpreted, whereas Rust is compiled, so you have that compile step in there before you can run your code. Python's unique white space indentation sensitivity versus Rust's curly braces is probably the most immediate difference you'll notice when looking at code. While Python is strong and dynamically typed, Rust is strong and statically typed, but there's a lot of type inference that goes on in Rust. So not everything has to be type annotated in Rust, but it is statically typed. Python chooses to have a large standard library, which has the advantage of having a lot of functionality available to you out of the box, but has the trade-off of being hard to change and maintain backwards compatibility within the language. Rust made a different choice to have a small standard library, which lets libraries do a lot of the iteration out of the standard library's backwards compatibility guarantees, but you then have to pull in a lot of external libraries to do things like generate random numbers or make an HTTP request. So there are trade-offs and different effects that that has on your code. The biggest implementation difference is probably that Python has garbage collection implemented with reference counting. Rust has you manage memory through the system of ownership and borrowing. It is more manual, and there's no garbage collection or anything running at the same time that your code is running. This is all at compile time. You have one variable that's an owner of allocated memory at any particular point, and other parts of the code can borrow that memory, and the Rust compiler uses that borrowing to check that nothing is, so when the owner goes out of scope, that memory gets cleaned up And the borrow checker makes sure that nothing is trying to use that memory after it's been cleaned up. So why should you learn Rust? One, if you're already comfortable with Python, you already like Python, why should you learn a new programming language? One reason is that you won't be alone. An interesting thing I found in our 2016 community survey, and I believe has been consistent in community surveys run since then, is that the vast majority of people who come to Rust are most comfortable with Python. So there are a lot of other people who have learned Rust after Python and find it to be interesting. I like to think that of Rust as being high level in the front and low level in the back, the mullet of programming languages, if you will. You get to write these high level ideas that you might be used to from Python, but you get a little bit more insight into the lower level control that you can choose to have and get different effects from your software. And Python, at some point, you get it as fast as it can go, and it just can't go any faster. This was an experience I had with Ruby. I was spending a lot of time trying to make Ruby run faster. And I found at a certain point, you have to drop into C to get more performance. But I'm terrified of C. And that's when I got into Rust. And similarly with Ruby, and with C, Rust has a C ABI, so you can call Rust from Python, and by putting Python and Rust together, you can get a lot faster code. So you can choose to use Rust in particular parts in your Python programs when you need that extra performance. And looking back at this chart of differences that we went through, the net effect of all of these differences are that Rust will make you think differently about writing code. It might make you write your Python differently. It might help you understand why Python works the way it does. It might help you appreciate the things you like about Python more. And it will just stretch your brain in a different way. In a way, like in a toolbox, you have a hammer and a screwdriver, and they're good for different things. In a toolbox where you have a Ruby or a Python, adding a Rust to that toolbox gives you different trade-offs that you can make in different situations. So I think it makes your toolbox, your programming toolbox, more well-rounded. This was just a very quick taste of Rust, and I hope I've piqued your interest. I will be doing a longer talk called Let's Find Out What's Special About Rust at a future live Manning Rust conference. So I hope to see you there. Thank you very much.
Today, we're going to learn how to solve mazes using Python. Now, there's many ways you can do that, but we're going to concentrate on 3 algorithms: depth-first search, breadth-first search, and A*. First, we'll learn how to actually create mazes and display them on the screen. Then we'll implement each of the 3 algorithms. Now, all of this is covered in my book, Classic Computer Science Problems in Python, in Chapter 2. But all the source code that we go through today is available for free in the repository linked to below. For our purposes today, a maze will be thought about as a 2-dimensional grid. There's a start location on the grid, and there's a goal location on the grid. And there are some parts of the grid that are inaccessible that we can't traverse through, that we'll call barriers. We can only move in the vertical or horizontal directions across the grid. And our goal is to get from the start location to the goal location. We'll look at multiple algorithms that allow us to traverse this maze. So we're actually going to go over quite a few different things today. First, we'll go over how to generate the mazes, and we'll also look at how to output them. And then we're going to look at our first maze-solving algorithm, which is supported by the stack data structure. Then we'll see the queue data structure and breadth first search, which in code is quite similar to depth first search. And then we'll see a priority queue and a really powerful algorithm that it supports called A star. You can see here how our mazes will look when they're output to the command line. So in the top left, I have an empty maze, a maze that doesn't yet have a path going through it. The start location is represented by S, the goal location by G, and the X's are barriers, places that we can't traverse through. Eventually, we're going to try 3 different algorithms for solving the maze. Each one of them is here in action on the same maze. So first we see depth first search, and the path that depth first search found is shown by the asterisks. Then we see breadth first search, again the path is shown with the asterisks, and finally we see the result of A star, again with the asterisks. Let's look at how we're actually going to build the maze in code. If you're following along in the online repository, all of this code is in the maze.py file in the chapter 2 folder. Okay, you've seen imports before. We need to use enums. We're using typing here. I use type hints throughout my code to try to make it more readable. If you haven't seen type hints before, they basically tell you a little bit about what a variable or parameter or return type is supposed to be without you having to deduce it from documentation or by reading the code. They can look a little verbose if it's your first time with them. There's a jump start for them for those of you that are reading the book in Appendix C. We're going to do some random number generation. We're going to need to use a square root function. And in a different file, we've defined depth first search, breadth first search, some helper functions, A star. We'll come back to that later. First, let's look about how we're going to actually define how a maze is structured. So a maze is going to be composed of cells. And a cell is actually going to be an enum because there's only really 5 possibilities of what a cell can be, and it's nice to actually explicitly write those possibilities out. So we could have an empty cell, that's a cell with nothing in it. We could have a block cell, a cell that we can't traverse. We could have a start cell, that's a cell where we would start a path from. We could have a goal cell, that's a cell that we want to get to from the start. Or we could have a path cell, that's our actual route for going from the start cell to the goal cell. Another helper class is called maze location. It just represents a location in the grid, a row and a column. We could have also done this using a pair, but we're doing it here using a named tuple. And a named tuple is just a tuple that has a descriptor for each of its components. So we have a row and a column. And then we get to the real meat of it, the class maze. So the constructor for a maze has a lot of default parameters. We're going to say by default that a maze is a 10 by 10 grid. We're going to say by default that approximately 20% of it is filled with blocks. That's going to be done using a random number generator, so it's not going to be exact. But every time we decide, do we want to fill this spot with a block or not, we're going to look at a number and see, is it lower or higher than sparseness? We're going to usually have our start location be in 0, 0, so row 0, column 0. And we're going to usually have our goal location be at location 9, 9, row 9, column 9. So when we init a new maze, we're just going to basically be filling in these parameters. Now, I use the convention of an underscore before a parameter name, before a variable name, if it's going to be private. So this is my own copy of rows and columns that I'm setting based on the parameters rows and columns. The rest of this is pretty self-explanatory. We use here a list comprehension to fill the initial grid completely with empty cells. And we have a helper method that's actually going to go around through every one of the empty cells and see, do we want to fill that in with a barrier? And that's what randomly fill does. It uses that sparseness parameter, generates a random number between 0 and 1.0 and sees, is it less than sparseness? So is it less than 0.2? Which means approximately 20% of the time we'll fill the grid with a blocked location. We also then set the start and the goal to actually be marked on the grid. And to do that, we use the cell.startEnum and the cell.goalEnum option to fill in the appropriate places in the two-dimensional list that makes up the grid. How do we actually represent a grid on the command line? Well, we print out the maze by going through every row and outputting every single value in that row as its string equivalent, joining them all together, and then just adding a new line character at the end of the row so that we go on to the next row. It's actually really compact. It's really nice here how quickly we can go from two-dimensional list to a string that actually can be outputted on the command line. What's goal test? Goal test tells us if some location actually is the place that we wanted to get to. And so we're basically just going to look, is the location that we're looking at the goal? What's successors? Given some location in the maze, what are the other locations that we can go to? So I told you earlier that in our grid, we're only going to be able to move horizontally and vertically. That means we can move one row down, or we can move one row up, or we can move one column to the right, or we can move one column to the left, and that's it. All that happens in successors is we try all four of these options, and the options that do not have a blocked location, that have an empty location in fact, in the area that we're going to, we are going to allow them, and we add them into a list called locations that we ultimately return that contains all of the maze locations that we can get to from some maze location. So where can I go from here? What mark does is it takes a list of maze locations and fills them in with asterisks, and then replaces the starting goal again in case the asterisk overlaid the start or the goal. So this is a way of, after we've actually solved the maze, filling it in with the path that we found to solve it, which is going to just be a list of maze locations. Clear takes a path and removes the path from the maze. The reason we might want to do this is because we might want to use the same maze more than one time to demonstrate how different algorithms solve the same maze, as we saw at the beginning. So clear goes through the path, sets every location on the path to be an empty cell, and then if part of that path include the starting goal, we still want to see where the starting goal are, so we put the starting goal back on the grid after we've possibly erased them. These next two methods, Euclidean distance and Manhattan distance, we'll come back to later today when we look at the A-star algorithm. In maze.py, we do have a little output that you can run already to start seeing how all of this fits together. What do? We create a maze, we try printing it out. That's that first maze, the empty one that you saw earlier on that didn't have a path in it. Then we start trying to run depth first search, breadth first search, A-star on the maze. We'll come back later and see these in action. All right, now that we've defined the maze, we're ready for our first maze solving algorithm. And our first algorithm is depth first search. Depth first search is about going as deep as you can and then turning back when you hit some place where you can't go any deeper. So in the example here, we keep trying to go the same direction. We're going up, 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 and then we hit this barrier. And once we hit the barrier, we can't go any further, so we have to backtrack to the last location. The last location where we could go a different direction was location 4. So we come back to location 4 after we've been at location 5, and now we try going a different direction. We again, when we go the different direction, want to go up, but we can't because there's another barrier. Then we tried the second place we tried last time to the right. Can't do that either. There's a barrier. So we try another location that we want to go, which is down. Now we have an option when we're here, so we can go to the right. That's our second choice always. Up was our first choice, but we had already been there before. So we continue on. Basically, the key point about depth first search is that every time we get to a point that we can't go any further, we backtrack to the last point where we could go a different direction, and we continue from there. This, as you might imagine, this is not necessarily the most efficient way to solve this maze. we will see other algorithms that give us the best way to solve the maze. For our purposes, depth-first search is just a way to solve the maze. To actually implement depth-first search, we're going to need a data structure known as a stack. A stack is actually pretty easy to imagine as a stack of papers in terms of how it works. Imagine we're grading an exam. We're getting the papers in. The first paper that comes in is from Ricky. And then we get our next paper in from Sally. And then after Sally, we get our next paper in from Vicky. And then after Vicky, we get our final paper in from Mark. Now note that Mark actually handed his exam in last. However, Mark is actually going to get his exam graded first because he has the first paper on the top of the stack. So the last paper handed in is the first paper that actually gets graded. Well, unfortunately for Mark, that was a really bad choice. Then we're just going to keep going backwards. So we end up going from the top of the stack to the bottom of the stack until we find the final paper, which was actually the first paper that was actually handed in. That's pretty amazing. So we say that a stack is last in, first out. In other words, the last paper that gets handed in is the first paper that comes out. Now that we've seen what a stack is, let's talk about how we can implement it in Python. So here we see what could be the elements in a Python list. Perhaps they're strings of single letters, and they're always being added in onto the right-hand side. You can think about the right-hand side as the end of the list. Then when we remove them, we're always removing them from the right-hand side. This is just like the stack of papers. The last item being added to the right is always the first item being pulled off from the right. So in a sense, we've just implemented a stack of papers by just always using the same side of a Python list. One final way of thinking about a stack that I'll mention is that the newest thing added is always the first thing taken off. So we're always removing the youngest, the newest items from the stack because they were the most recently added things. Here's an actual code implementation of a stack in Python. And it's really easy to implement a stack in Python because you can use a list as a backing store, and list has some built-in methods that make it really trivial to implement a stack. So don't get too worried by this generic T part up here that's part of the stack. That's a type annotation, and what it's saying here is that a stack is of some type. So it's a stack of integers, or it's a stack of strings. And the list is actually going to have the same type, of course, because it's the backing store. So it's a list of integers or a list of strings that's backing up the stack of integers or the stack of strings. Two key methods, and we're going to see these again in both a queue and a priority queue. Push is for adding an item onto the stack. Pop is for removing an item from the stack. And they make use of some methods built into lists in Python that make this really easy. Append will always add an item onto the end of a list. You can think about it again as like the right-hand side of the list from our diagram. Pop removes and returns an item from the right-hand side of a list. And so we're just calling pop on a list here to implement pop for the stack. Then we have two other pretty trivial methods. Empty just tells us, is there anything left? And we just check to see, is the list still valid? And representation, we're just going to return the representation of the list that backs the stack. So really easy to implement a stack in Python by just using a list and a list's built-in methods, being really sure that you're always adding and removing items from the same side of the list. Now that we understand stacks, we're almost ready to implement depth-first search. I've implemented a graphical user interface version of our program using tkinter to illustrate depth-first search, and later on we'll use it again to illustrate breadth-first search. And I'm going to put a link below the video so you can check out the repository with the tkinter source code if you want to mess around with it. The code is really similar to the code we're going to look at a little bit later, except for that it adds all these tkinter GUI components. Before we actually run it, let me tell you a little bit about the two data structures that we're going to need to implement a depth-first search. The first one is a stack of states. You can think about them as places that we're considering searching. And we can call that the frontier. And we're actually going to implement it using a stack, which we just implemented in Python. And the other data structure is the set of states that we've already searched. And we're going to call that explored, and we're going to implement that using a Python set. As long as there are more states in the frontier, that's the places we still are thinking about searching, the depth-first search is going to keep checking whether they're the goal. If a state is the goal, the depth-first search will stop and it's going to return that state. If it's not the goal, what it'll do is add all the successors of that state to the frontier. And we saw earlier in the maze class how to find the successors of any given cell in the maze. We're also going to mark every state that we visit as having been searched in the explored set. That way, we're not going to get caught in a circle going back around and again to states that we've already searched. So Explored is just keeping track of, hey, we've already been there, don't need to go there again. If at some point the frontier is empty, it means there's nowhere left to search, and we're done. We never found the destination if we get to the point where the frontier is empty. Okay, let's try running this. Now, what you'll see here is red is our goal, black is barriers, white are empty places we haven't been to, and green is where we start from. So I'm going to run it now. What you're seeing in orange, that's the frontier. And you're also seeing on the right-hand side, I know the text is a little bit small, but on the right-hand side, those are items being added to the frontier. But notice, as blue moves, blue is the current node that we're on. We actually are removing an item from the frontier. So every time we go to a new place, we're going into the frontier, which is a stack, and we're saying, hey, pop the next thing off the stack, let's go search from there. And then we continue to move. Now, what you'll notice about us moving along here is that we're not actually going in any kind of targeted way towards the goal. We're not using any information about the goal to direct ourselves. We just keep continually moving to the next place on the frontier, and that's going to be the last place added to the stack. Remember, a stack is last in, first out. So we're continually adding new items to the end of the frontier, and then that last item added to the frontier is the next one we explored. But we're also adding a couple other items every time, right? Because everywhere we are, there's another, usually up to 3 items that we could be adding to the stack, but we're only looking at one of them each time. And so we're actually adding more items to the stack often than we're removing from it. And so our frontier a lot of times is growing, but every time we go to a new place, it's shrinking. Now, you'll notice we actually missed the goal here, right? Because again, there's nothing directed here about which way to go. We're just always going to the last item added onto the stack, which there's really no intelligence to. We just keep adding whatever items are next to the current node to the stack. Once we hit a dead end, we end up going back to the next item on the stack. So that's going to be an item we saw earlier, and we didn't end up actually going to right away because we went to the item that just happened to be at the end of the stack. Now we got to an item that actually got us to the goal. And so what gets illustrated for us in the end here in cyan, which hopefully you can see here, this is the cyan path here, is our path that we found using depth-first search from the start to the goal. And how do we generate the path? Well, every item that we came to, we marked the node that we got to it from. And so then we can actually work backwards. When we get to the final goal, we can look backwards, oh, we got to the goal from this node, and when we actually put this node onto the frontier, we marked, oh, we got to that node from this node, oh, and we got to this node from this node. So then when we get to the goal, we can work backwards along the whole path. Now, look at this path. It's not very good. Why is it not very good? It's going totally out of the way to the right here into kind of this useless area that is totally blocked off before coming back around and going all the way to the left to get back here to the goal. It's definitely not the shortest path to the goal. So that's something that you should know about depth-first search. Depth-first search does not give you necessarily the best path, as in the shortest path to the goal. Notice also that there's actually some parts of the board or the maze that we never actually explored. These two white cells over here, we never actually got to them. If we hadn't found the goal, we would have eventually gotten to them. But because at some point we found the goal, we stopped the search. Okay, one more data structure, and we're going to reuse this data structure for breadth first search and also for A star, a node. And it just represents a point in our search. So it could be the current location in the maze that we're looking at right now. So what is a node? A node is going to have some kind of state associated with it. In our case, that's going to be the class maze location that we looked at earlier. So basically a combination of a row and column makes up the state of some node in our maze. And it also have a parent, and that's the node that got us to this node. Now, the node that got us to this node might be no node if this is the first node in the search. So for example, the starting location where we start in the maze. That's why this is an optional. An optional is an item that either has a value or does not have a value. And so we might mark it as none, the parent, if this is the first node, if this is the start node. There's two other parameters here we're not going to use for depth first search, but because we want to reuse the same node class for A star later on, we need. Cost and heuristic are two values that we will use later on for A star, but you don't need to worry about till later in the video. So all you need to know right now is that a node is composed of basically a maze location, that's its state, so some point in the maze, and some other node that got us there, so the maze location that we got to this maze location from. Less than again is implemented again for A star, and we'll come back to it later, but basically we can just sort two different nodes by seeing how much the cost plus heuristic of one is compared to the cost plus heuristic of another. And the one that has the lower combination of cost and heuristic is the node that we say comes first. And you'll see how that's useful later on in A star. Okay, we're ready to actually look at depth first search. We made it. It's a lot of buildup to get here, but here we are. Depth first search, what does it take? It takes an initial state, so that's going to be where we're starting from. So usually the starting maze location will be that initial state. It takes a goal test function. That's in Python type hints called a callable. And that goal test function is going to look at some nodes and tell us, oh, hey, is that the actual place we want to get to? Is that the goal in the maze? And it's going to return a Boolean, which is going to be true or false. Successors is again a function, that's what a callable is, which is going to tell us from this current maze location, where else can we go to? And if you remember earlier in the maze class, we implemented a successors function. And that just told us from this maze location, these are the other maze locations that we can get to. And depth first search as a whole is going to return either the goal node, so that means we got to the goal node. And remember that the nodes know their parents, so we can recreate the path just from the goal node all the way back to the start node. Or it could return none if there was no way to find the goal node, right? It's possible that the goal is surrounded by barriers and we couldn't get to it. Or even the starting location is surrounded by barriers. Or just somewhere there's some barriers we couldn't get through to get to the goal. So we could be returning none, so that's why we're returning an optional here, because it could be none. Okay, let's look at depth first search's actual code. So we mentioned earlier the two data structures, frontier and explored. Frontier is where we could go explore next. We haven't explored the places on the frontier yet, but we could explore them in the future. We could kind of go to them and see what's up and see if they're the goal and see who their successors are and add their successors to the frontier. And the frontier is a stack. So the last item that we add to consider looking at is the first item we're going to actually look at next. Explored is a set. It's the places that we've been, so we're not going to go to them again. Really simple. Don't want to repeat ourselves, don't want to go in circles. Okay. And then look how little code it is for depth first search. This is the whole actual search, and there's really not that much to it. In fact, there's probably almost as many comments here as there are lines of code. So we're going to keep searching as long as there are still places to search. So while the frontier is not empty, as long as there's still things on our stack, we're going to keep popping them off the stack and saying, hey, I want to see what's going on with you. Are you the goal? And when there still are places to look at, that's exactly what we do. We pop the next thing off the stack. That would be the last one added to it. We look at its state. So that's the maze location, basically, right? We check, is that the goal? If that's the goal, we're good. We're done. We found the end. If it's not the goal, then we want to look, where can we go to from this place? That's successors. Successors is where can we go to next? If we have already explored that place, well, then that's not that useful to us, right? We don't want to go in circles. So we're just going to go continue, which takes us back to the top of the loop, and we'll look at the next child, the next thing in successors. However, if it's a place that we haven't been to yet, well, now we have been to it, and we've added it to explored, and we've also now put it onto the end of the frontier, and that means that we will now actually go to it at some future point unless we find the goal first. Now notice we're adding all the children from successors to the frontier. So each time we go to a new node, we could be adding up to 3 other nodes, right? We're looking to the right, we're looking to the left, we're looking up, we're looking down. We came from one of those directions, so we're not adding the direction that we came from to it, but the other 3 locations we could be adding to the frontier. So that's why we have to go through all the children, all 3 of them, and add them. And then just the last one that we added, because it's a stack, is the first one that when we get back up to the top of the while loop, we're going to pop off. If we went through this loop, we went through everything on the frontier, we searched through everywhere, we kept adding everything, and we never found the goal, because when we get to the goal, we return, right? If we went through this whole loop and we never found the goal, then we return none, meaning there was no way to get from the starting location going to node, successors, adding them to the frontier, and actually get to the goal. So that just means there's no solution to this maze. One helper function, really simple, is going to help us get the path from the node. I mentioned earlier how every node keeps track of its parent. And the reason that's so important is it means once we return the goal node, or we return the node that's at the goal, we can actually go and work backwards all the way back to the start node. And that's exactly what node to path does. It just takes the goal node, or the last node we want to work backwards from, and then it generates a path by looking at the node's parent and saying, hey, parent, let's add you to the path, and then let's look at your parent, and then let's look at the parent of your parent, and then the parent of your parent of your parent, etc., until we get to some node that doesn't have a parent, which is presumably the start node, and then we just take that entire path and reverse it, and we have the entire path. So we can run our depth first search on a real maze. We here back in maze.py generate our maze, we print it out, and then we try finding a solution from the start goal to the end goal. How do we do that? Well, we generate a solution by calling depth first search, passing it the maze's start, passing it the maze's goal test function, passing it the maze's successors function, and we see, did depth first search return a actual result? If it didn't, it's going to be none. And if it's none, that means we didn't find a way to get from the start location to the end. But if it did, we get that path by calling node to path on the solution, which, remember, the solution, it's an optional because we could have found a node or we could have found nothing if there was no path. But if there was a node, we generate a path from the node using node to path. And then we mark it in the maze, we print out the maze, and then we clear that path from the maze. The reason we clear it from the maze is that then using the same maze later on, we'll mark it with breadth first search and with a star. Let's just look at that mark and clear method really quick. So what does mark do? Again, mark goes through a list of locations in a path and says that each of those locations in the path should actually be marked as part of the path inside the grid. So if you remember, our enum called cell actually has a path option. And so we're saying here in the grid, hey, mark all those places that are on that path from start to goal. And then we just make sure that we set the start and the goal on top of the path, because remember, the path is going to include the start and the goal. So we want to overwrite them with the start and the goal. And in clear, we're basically just reversing this. We're going through the path and marking them all as empty instead of as path. And then we're going in again, because we might have overwritten the start and the goal with empty. We want to then make sure that start and goal actually appear. So we're putting start and goal back in. So now we can actually run. Let's try it. And we did this at the beginning, right? But we can actually see a path here that was actually generated from our code. Here's when we printed out the blank maze. And then here is our actual depth first search path. And again, you see not the best path, right? Just when we looked at the graphical version, right? We're going kind of all over the place here. We go all the way to the right, then we end up going almost all the way to the left, then we end up coming back to the goal. Not the shortest path. So let's now transition to an algorithm that actually can give us the shortest path, breadth first search. And just as a quick preview, you can already see here in the breadth first search result that we're getting a much better path. In fact, this is the shortest path from the start to the goal. Now, there might be two paths that are equidistant from start to goal. So this is the most efficient path we can find, but we could find maybe another equally efficient path. But it doesn't mean that this is not the most efficient path, the fact that there's another one that's equally efficient, right? So anyway, breadth first search, you can see, gives us much better paths than depth first search. What I think you're going to find amazing is just how similar the implementations are. But to get to that, the first thing we need to do is find out about queues. We've all been in queues before. In the United Kingdom, they call queues what in the United States we typically call lines. So in the US, we might say you've been in a line to go to the bathroom, and you wait in line at the store to check out, or you wait in line to get your car serviced, whatever. So in some other cultures, they call that a queue. And basically, in a queue, the first person who gets in line is the first person who gets out of line. So we say a queue is first in, first out. Let's just model it here. So we have a monkey who is selling flowers. Maybe it's the monkey flower store. And this blue cat is the first one to get in line at the monkey flower store. And following that is this white, some kind of animal, I don't know, perhaps a sheep. The white sheep gets in there after the blue cat. And then the beige bear, I suppose, gets in there in line after the white sheep. And finally, the green cat gets at the end of the line. Now, who's been in the line the longest? Well, actually, the blue cat has been in the line the longest. The blue cat was the first one in the line, so the blue cat is actually going to be the first one to get out of the line. Therefore, first in, first out. The blue cat loves the color blue, and it gets its pick of flowers because it was first, and it gets this beautiful blue flower. Then the, whatever we're calling it, a sheep or something, is next in line, so it gets whatever flower it wants. It gets the red flower. And as we see, actually the last item to get in was the last item to get out, which is the opposite of a stack. In a queue, we're first in, first out, so last in was actually last out. Like with a stack, we can use a Python list to model a queue pretty easily. And all we need to be careful about is which side we're pushing to and which side we're popping from. So as you can see in this example, we could keep pushing to the right-hand side. But then when we remove elements, we should remove them from the left-hand side. That way, the oldest elements are the first elements to be removed. First in, first out. The first elements to get in there are the first elements to get out of there. Does that make sense? Let's now see it in code. We're back in generic_search.py to look at the queue class. It's very similar to the stack class that we looked at earlier. It just has two changes. If you remember, our stack was backed by a Python list. Well, instead, our queue is backed by a Python deck. The difference between a list and a deck is that with a list, it's very easy for us to add and remove to the right-hand side. With a deck, it's easy to add and remove from either the right-hand side or the left-hand side. which brings us to the other difference. Pop on the stack was using a list and calling the pop method on list, which removes from the right-hand side. Dec gives us a pop left method, which removes from the left-hand side, therefore allowing us to push to the right-hand side, still using append, and then pop from the left-hand side using pop left. This is the only difference between the queue and the stack, but it makes all the difference in terms of ordering. By changing the side that we pop from, we go from doing last in, first out, as in a stack, to first in, first out, which is what we want for a queue. The rest of this class is the same as a stack. We're back here in our graphical version. Again, you can find the source code to this in a repository linked to below. Now, I've left up the version of the depth-first search solution that we looked at earlier, and you might remember this path was pretty convoluted. Look at how many items also were on the frontier that weren't yet explored when we got to the destination. Two interesting notes I want you to remember. Depth-first search did not give us the best path, and it always had a lot of things on the frontier that we hadn't yet gotten to. Let's now try the same maze using breadth-first search. Now, breadth-first search is going to be a lot more systematic. In a depth-first search, we kind of just kept going whatever way we wanted to go, and when we hit a barrier or we got to a point that we couldn't go any further, we went back, we backtracked to the last point that we could, where we could have gone a different direction. In breadth-first search, we're carefully going just a little bit further away, like 1 unit, you can think about it, further away from our start with every progressive move across the maze. So we keep looking 1 further away from the start, and then we look at all the locations that are just 1 further away from the start. Then we look at all the locations that are 2 further away from the start. Then we look at all the locations that are 3 further away from the start. Then we look at all the locations that are 4 further away from the start. Pay attention to the orange nodes. The orange nodes, again, are the frontier. And you can also see the frontier. It's a little hard to make out because the text is a little bit small on the right-hand side, but you can see the frontier growing and shrinking as we add things to it, as we explore new items on the frontier and look at their successors, and remove items from it as we actually go to those items on the frontier, pop them off, and look at them. So our frontier is never getting that big here, but we're continually going to items that are very systematically on the frontier, just a little bit further away from the start. And what that means is we're going to have looked at every node at a point where it was as we got to it from another node that got to it from another node that was as close to the start as possible. In other words, every node that we're on popping off of the frontier here and then exploring, we got to from a node that was as close to the start as possible when we first explored it in terms of who its parent was. Did I say that in a clear way? In other words, every time we're looking at another node and looking at its parent, we're always looking at the node that is just 1 further away from the start. What does that mean? Well, look at this right here, this final solution. This is a great solution. This is actually a way better solution than we found with depth-first search. We didn't go all the way to the right like we did in depth-first search, then come all the way back to the left, and then finally find the pathway to the goal. We found the shortest possible path to the goal this time. And that's because we did that very incremental unraveling of the frontier. By continually going just a little bit further out from the start, we were able to, every time we hit a new node, have the most efficient path from the start to that node because we so carefully unraveled 1 step at a time. And so therefore, when we finally got to the goal node, we had a complete path all the way back that was as efficient as possible because it was built by continually going just a little bit further away and keeping track of how we got just a little bit further away by marking that parent. So this is a really good solution, and look also how small our frontier is, contrast that with depth first search, we actually ended up exploring more nodes here with breadth first search than we did with depth first search. Now, you might say, okay, how much does that really matter? Because we still explored almost everything with depth first search. It's really going to depend on the context of the particular maze, and there might be situations actually where you get lucky with depth first search and you find the goal really, really fast, but there could also be situations where, let's say the goal was over here, like quite close to the start, and with depth first search, you ended up going like all the way over here and coming back, whereas with breadth first search, you would have found it quite quickly. So the individual maze is really going to dictate what actually gets there faster, the depth first search or the breadth first search. But breadth first search will always find the most efficient path from the start to the goal, and depth first search will not necessarily find the most efficient path from the start to the goal. So if we're looking for efficient paths, we always want to use breadth first search over depth first search. But later on, we'll look at an even more efficient algorithm, so one that finds the goal as quickly as possible while still finding the most efficient path, called A star. We're here looking at the code for breadth first search back in generic_search.py. This is probably the most important moment in our entire video. Here's why. This code is identical almost to the code we looked earlier at for depth first search. Really. Every line of this is exactly the same as the depth first search code, except for this first line. The frontier here is a queue instead of a stack. Just making that one change completely changes how the search progresses. Instead of the search going down some long path, and when it gets into some dead end, backtracking to the last point it could have gone a different way, the search is going to be systematic, continually going just one node further away from the start until we find the goal, and therefore finding the most efficient path. Just by making that one change from stack to queue. Do you believe me? Go look at it yourself. Look at generic_search.py in the repository where all the code for this video resides. Here's depth first search again. Frontier's a stack. The rest of this code is completely the same. Let's look at breadth first search again. The code is completely the same except for that the frontier is a queue. Just doing first in, first out instead of last in, first out completely changes how we pull items off of the frontier. And by completely changing the order that we pull items off of the frontier, it completely changes the order that we explore the map. And by changing the order that we explore the grid, changes the order that we will get to set each parent of each node by. And that will therefore lead us to finding the parent that's just a little bit further away from the start each time. And then when we get to the goal, we will end up with a chain of parents that takes us in the most efficient way possible all the way back to the start. But the key insight is all we changed is the data structure. The algorithm actually stayed the same. The algorithm's the same, it's just having a smarter data structure. Pretty amazing. So I don't really need to go over this again because we went over all the rest of this with depth first search. There's not really anything to add. This is literally the same. Back here in maze.py, and our code for testing breadth first search is also the same as our code for testing depth first search. So all we're doing is we're calling BFS here instead of DFS. You know, come to mind, we could actually have combined BFS and DFS into a single method and just had an if statement that decided if we were going to use a queue or a stack, depending on some parameter that would set whether this is a breadth first search or a depth first search. But anyway, we did them as separate methods for clarity. And you can see here that this is, again, pretty much identical code. Let's actually run it, see the results again. We looked at them earlier, but we know that this is the original map here with nothing on it. This is the grid with depth first search on it. And look, it didn't find a really great path. It's kind of zigzagging left and right? And here we are in breadth first search, and it found a superb path, as efficient as possible on the same exact grid, but this time without zigzagging. Just get me to the destination as efficiently as possible. And soon we will look at A star, which gives equally efficient paths, but does it in a more efficient way, actually finding them. And so you notice these two paths are actually different because A star and breadth first search do operate differently. However, they both find equally efficient paths. It's just that A star finds the most efficient path more efficiently. So the algorithm itself actually doing the finding operates as efficiently as possible. We've looked at several different data structures and we've seen how they've enabled different algorithms. The stack enabled depth-first search, which was the first maze-solving algorithm that we looked at. We saw it had a couple issues. Then we saw how we could easily change from a stack to a queue, and that would totally transform our search into a breadth-first search, which found the most efficient path. Now we're going to introduce another data structure, priority queue, and it's going to enable yet another algorithm, and this will be our most powerful algorithm yet, A star. Our analogy for a stack was a stack of papers. For a queue, we thought about a line in a restaurant or a store. When I think about priority queues, I like the analogy of a letterbox. The thing that really distinguishes a stack from a queue is the order that we remove things from them in. So with a queue, we remove the first thing in first. With a stack, we remove the last thing in. That's why a stack is last in, first out, and a queue is first in, first out. Another way to think about removal could be by priority, and that's the purpose of a priority queue. Think about your mailbox, whether that be your digital mail, your inbox and your email, or the letters that you get in the physical mail. When you open them up, I bet you don't always just open them up in the exact order that you receive them. For example, if this was some letters that I received, I won't necessarily open up the spam first. Actually, it's much more likely I'd open up the thing that said urgent on it. At least that's what I do usually. And maybe after that, after I opened up urgent, I would then open up royalties because I like getting my money. And then, bills are important, so I might open that, and probably I'd open up the spam last. So the order that I took things out of this data structure was based on something innate about each of the items, which was how important they were to me. So we could say that that importance is their priority. So all a priority queue is a data structure where we remove things based on their importance. In a priority queue, every individual item has some kind of priority, and that priority determines when we take it out. In this example, each item has a numeric priority, and we're going to take out the items that have the highest priority first. So instead of it being the left-hand side that we remove from the right-hand side, it's just any item in there. First we removed the 9 because that was the highest priority, then the 8 because that's the second highest, then the 6 because that's the third highest. We could also do this in the reverse, and we'll see that a little bit later in our real example, where we use the lowest priority item first. All right, we're back here in generic_search.py, and we're looking at the priority queue. Now, the code for priority queue, again, is very similar to our code for queue or stack. But our priority queue, while being backed by a list, is actually controlled by two functions from the heap queue module in Python. And the heap queue module allows us to use a Python list as what's called a heap. Now, the data structure heap is actually beyond the scope of this video. We can't just cover absolutely everything. But let me just tell you that a heap is a standard way to back a priority queue, and it allows us to quickly access either the minimum or the maximum element within the list by keeping the list ordered in a very specific way. That again is slightly beyond the scope of our video today. But we just make use of these heap queue methods, heap push, which makes sure the list is ordered in a specific way so the maximum or minimum item is easily available, and heap pop, which then removes that maximum or minimum item. So in this case, the default heap push and heap pop are actually going to keep the minimum item easily accessible, which is what we will need for A star. Now you might wonder, how are we figuring out what's the maximum or minimum item? So we're putting items in here, and if you remember earlier, we defined the node class. And you might remember I talked a little bit earlier about why we defined the less than sign, because we're going to need it later for A star. That's going to allow our heap push method and heap pop method to be able to compare two different nodes to one another and figure out which is the quote-unquote smaller node by combining the cost and heuristic. So we'll figure out which is the node we want to go to next by looking at which is the node that's the smallest, and that's going to be the node that we get back from our priority queue when we call pop. So we're going to end up ordering by which one we, sorry, I went to queue. Let me go back down to priority queue, which one we want next. We're going to end up making sure that the one that has the lowest value is the one that we get out next. I'm looking back at our solution to breadth first search, and one thing we like about breadth first search is that it's very systematic. We kept looking just one node further away from the start till we got to the goal, and that meant that we definitely found the most efficient path to the goal. But it also meant that we searched some nodes that were really pretty unnecessary to search. We searched nodes over here in the top right, we searched nodes over here in the bottom left. What if we use some intuition about where the goal is to help us steer and direct the search? That's what A* does. A* says, why don't I use an estimate of how far a node is away from the goal to see if that's a node I actually want to explore next? So for example, when making the decision whether to explore this node versus this node up here, they both might be equidistant from the start. But if I use, let's say, an estimate of distance, we could use Euclidean distance here to see that this node is definitely closer to the goal than this node is, then I can automatically choose to go to this node and not waste my time going to this node. In many cases, almost all cases, this will actually lead us to more quickly finding the goal. So we'll still get a super efficient path, the most efficient path, just as we would with breadth first search, but we're actually going to do that quite a bit faster. And that's the really nice thing about A* is how those heuristics guide the search. Now, there's more than one heuristic that you can use, but we're going to go over two specific ones that you can use within a maze. And before we do that, let's look at just a little bit of math that underlies how we're going to make these decisions about which node to search next. When we consider which node to take off of the frontier in A* search, we're going to look at every node on the frontier's f of n. What f of n is the estimate of which node, of what the cost of this node is, which is a combination of what the cost has been to get to that node so far, plus our heuristic cost, which is our calculation of how far approximately is this node from the goal node. We combine the cost to get to this node so far with our estimate of how far away it is from the goal node together to get the node's cost estimate, the f of n. And the node with the lowest f of n is the node that we're going to explore next. So the node, in other words, that's going to help us get the lowest cost path to the goal is the node that we really want to go to next. This is, in other words, directing our search towards the goal in the most efficient way possible. So what is a heuristic? Well, a heuristic is an intuition about the way to solve a problem. In the case of maze solving, a heuristic aims to choose the best maze location to search next in the quest to get to the goal. It's an educated guess about which nodes on the frontier are closest to the goal. If a heuristic used with A* produces an accurate relative result and is admissible, that is, it never overestimates the distance. That's key. We don't want to have any heuristics that overestimate the distance. Then A* will deliver the shortest path. So if we have a good heuristic, we'll get the shortest path. The heuristics that calculate lower values leading to a search through more states, whereas heuristics that are really close to the exact real distance but don't go over it because that's inadmissible, lead to a search through fewer states. Therefore, ideal heuristics come as close to the real distance as possible without ever going over it. We're going to look at two really good heuristics. The first one here is Euclidean distance, and you're familiar with that. That's just the distance formula. You draw a line on a map and you see how long that line is. And you can use Pythagoras' theorem to figure that out. And here we see an even simpler heuristic. It's called Manhattan distance, named after Manhattan, a borough in New York City that's roads are almost completely on a grid system. Manhattan distance is just how many rows up or down or columns left and right do I have to move to get to my destination. Here we see the code for our two heuristics. This is in maze.py. So let's start with Euclidean distance. Now, what it takes is the goal, which is a maze location, and what it returns is a function that, given a different maze location, tells us the distance to the goal, which is going to be a float. So this is actually a function that returns a function. Sometimes you might want to use that idiom for situations where you want to have a function that's pre-configured that you get back that can do something for you. And in this case, we want a function that's pre-configured to calculate distances to the goal. So that's actually pretty convenient. How's this inner function work? Well, given some other maze location that we want to calculate to the goal, what we do is we find the difference in x's between that other maze location and the goal, the difference in y's. This is just the distance formula from grade school. Do you remember this? We multiply the difference in x's with itself. We multiply the difference in y's with itself. We add those differences together and take the square root. This is literally how you find the Euclidean distance on a piece of graph paper, just as you remember it. And then we return that distance. And what we get back is something that's really going to be able to guide our search by hopefully just drawing those straight lines to the goal and seeing, hey, which line is the shortest? Now, down here we have Manhattan distance, and this one's even simpler. Remember, Manhattan distance, we're not even looking at a straight line. Well, we're looking at instead set of kind of like an L shape of where we're going to go a certain amount horizontally and a certain amount vertically. And so this is really similar, the difference being that when we do the calculation, we just subtract the columns from the location that we're going from to the goal, and we subtract the rows from the location that we're going from to the goal, and then we add those differences together and return them. Really, really simple. This is actually an easier calculation. You could imagine how this being a simpler calculation might be a benefit if we were working in a really, really, really big maze and had to run this calculation a lot. But in general, on any modern computer, probably the difference for most mazes would be pretty negligible. All right, we made it to A star. Here we are. This is a popular algorithm. You know, this is an algorithm that's used in the real world all the time for games, for example. When you're in a video game and maybe you're on a map and you need to get from one part of the map to another and it automatically figures out the best route, A star used all the time, used in directions applications all the time. Really popular algorithm. Anyway, what you might notice right off the bat is that it's not that different from the depth first search and breadth first search algorithms that we've already looked at. In fact, again, we'll have a frontier and explored. I'll explain how they're slightly different than before, but it's really the same type of data structures. And actually, most of this code is, again, really, really similar to breadth first search and depth first search, which is pretty remarkable when you think about how different they all work. But first of all, we have one extra parameter up here, the heuristic function, which again is going to be a callable in our type hints, meaning that this is a calculation that, given some node, gives us back a float saying, hey, how far is this approximately from the goal? So we might be passing in either Euclidean distance or Manhattan distance as our heuristic. Then let's look at our frontier. So we've gone from using a stack or a queue to using a priority queue. That's because, again, when we have the frontier, we want to choose the nodes that have the lowest distance to the goal in total cost. That's the F, which is a combination of G, which is the cost to get up to that point where the node is right now, and H, which is the heuristic that tells us approximately how far is that node from the goal. So combining G and H together as F, we want the lowest F off of the frontier. The priority queue is going to give us that, which is great. The first thing we put on the priority queue is a node, as we have been doing in the other two algorithms, but this time we're actually using those two other parameters. Remember, much earlier on, let's go back to the code for a node. And if you remember, much earlier on, we were talking about the code for a node. I said to you, hey, cost and heuristic, I want to reuse the same node class, again, for depth first search and breadth first search that we're going to use in A star, but don't worry about them until we get to A star. Well, now we're worrying about them. So cost is G. Cost is how much did it cost to get up to this point where this node is so far. And then heuristic is our estimate of how far this node is away from the goal. So every time we create a node in our A* search, we're always going to set cost and heuristic, and we'll look at how we're going to do those in a minute. Going back, so our explored now, you'll notice, has also changed. Explored in the past was a set when we did depth first search and breadth first search. Here, it's actually a dictionary, and it's a dictionary that maps between our state and a float, which represents the cost so far. So the cost so far is actually pretty important to us because we want to be able to see what the additional cost would be to get to this node with the heuristic that we combine. So we're basically like storing the F in this explored list, because it is possible that we'll come around to it again and find a shorter way to get to it. So we need to actually keep track of what was the cost to get to it the way that we've gone so far. So let me just summarize that one more time. Explored is keeping track of how much it costs to get to the node that we have explored, so that if we end up finding it again, before we said, oh, we've already explored this node, let's not bother with it again. But this time we're going to say, oh, we've already explored this node, but hey, we found a shorter route to it. So maybe we do want to explore it again. Okay. So we've seen this before. We keep going as long as there's still things in the frontier. That's nothing new. We pop the next node off and we get its state off of the frontier. That's also nothing new. It's exactly the same as in breadth first search and depth first search. The only difference here is, again, that frontier is a priority queue. And so we're popping off the node with the lowest F every time that we're popping, instead of just the node that was the last one added or the node that was the first one added, like in our stacks and our queues. Here we're actually using some intelligence to pop off the next node, and we're using that less than calculation back in our node class, which I've gone over a couple times in this video, to actually calculate which node is the node with the lowest F. So that's basically what this less than is telling us. It's telling us, does this node have a lower F than this other node? Oh, if it does, we're going to prefer it. Our goal test is exactly the same as in depth first search and breadth first search. And so is looking at successors. We're still going to go to each of the successors and try to add them to the frontier. Then this next line's a little bit different. How do we figure out what the cost to get here so far is for each node? Well, because our maze doesn't really consider like some paths more difficult than others, we think moving is always about the same difficulty to move from one node to another. For the purposes of our maze, we just add one. So we just say, oh, this new node that I found, this child of the last node, is just one space further away from where the last node was. And so we just add one to get that new cost. Then we check, is this a place that we've been to before? Well, if it is, we might not want to explore it unless if it's a place that we've been to before, but we've now found a lower cost to get to it. If that's the case, we want to say, hey, I found this new great cost, so in Explore It, I set that cost, and then we're actually going to put it back on the frontier because we do actually want to explore it. So if it's either a place we haven't explored before, or it's a place that we've actually found a shorter way to get to, we want to explore it, so we put it on the frontier. Then we go back up to the top and we do it all over again. Again, this code, look at it. It's so remarkably simpler than you might have expected because it's so similar to DFS and BFS, which are pretty easy to understand. The main difference here is really, again, the data structure. It's the fact that our frontier is a priority queue, and that changes everything. The order that we take things off of the frontier is dictated by whether we're using a stack, a queue, or a priority queue. And that totally changes how the search progresses. Let's actually try running it and see what happens. Now, we've already done this earlier today, so I'm going to go out of generic search.py back to maze.py, and we'll actually try giving it a run. And I just want to remind you that this will find us the best path. This last one here is actually a star. And breadth first search also found us an efficient path, but A star is going to do it while searching through fewer total places. And that is great, because imagine that this was not just a 10 by 10 maze. Imagine this was a 1,000 by 1,000 maze. Well, then actually searching unnecessarily through some of the nodes we didn't need to search through might be a real problem that we don't want to waste our time with. So A star is our super algorithm. It's our algorithm that both finds us the most efficient path, and it also finds that path in the most efficient way. All right, there's 3 things I really want you to remember about what we went over today. The first is that depth first search and breadth first search are exactly the same, except for the data structure. We just changed the stack to a queue, and suddenly we went from depth first search to breadth first search with the rest of the code identical. The second, breadth first search and A star are going to give you the most efficient path from the start to the goal. That's pretty different from depth first search, which is going to just kind of take a stab in the dark at whether this is a good path. And the last thing, A star uses a heuristic to more quickly find the path to the goal, which is really useful on bigger mazes. Thanks for watching. I plan to do a lot more videos like this, so I hope you're going to subscribe and like this video. Also, I hope you'll buy my book, Class Computer Science Problems in Python. But even if you don't forget that all the source code is available for free in the repository linked to below. And you can also follow me on Twitter. I'm at Dave Kopec, DAVEKOPEC. Until next time.
I'm Olga, Senior Data Analyst, and we will be talking with you about exploratory data analysis with Python. A very popular topic, very common, people love to talk about it, everyone knows it. So in my talk today, I wanted to be more practical and focused on specific steps and commands for EDA in Python. So our agenda would be, we'll start a general overview, what is EDA, when it's good to do it, why people do it, and then go over some common Python hacks, common EDA mistakes, which I keep seeing data analysts doing, and review some other exploratory tools and applications. Okay, so let's start. Exploratory data analysis. Very common, you might run into it when you're preparing for an interview, and the companies might send you a data set and they will ask you to do EDA and then send results back to them. When you're already working on a project, less likely you will be doing EDA as often as you think. Usually your analysis will be very focused. It's going to be a deep dive or ad hoc or initial analysis. You're going to do EDA when you're new to a data set. So to answer when people do EDA, it's a first brief look at your data set, which usually happens before setting assumptions. After you set an assumption, then another stage analysis comes. Then you work on the initial data analysis. So why we need to do EDA? Data never clean. It comes in all shapes and conditions. And if you want to do a deep dive or any machine learning or data processing, you need to prepare your data for that. And that's where EDA comes to play. It helps you to understand what you need to look for, what data you need to clean, what is the relationship between different features, what are the patterns, what are the trends. Okay? So how to do EDA? There are a lot of tools out there. Python is becoming more popular and more common for data analysis. It allows you to do a variety of different things. So in my talk today, we're going to review helpful Python packages and common commands. I think I wanted to spend some time also discussing why Python and not something else. You can do EDA everywhere and using anything. You can do it in SQL, you can do it in a spreadsheet, you can do it in Excel, you can do it in any programming languages, you can do it in SQLite. Python is the most common one for a few different reasons. First of all, it's very easy to do it and learn because Python has so many built-in nice packages, which can help you with visualizations. Second reason is that data doesn't always structured. It's nice when it's structured, then you can apply SQL and just use Excel. When data is not structured, you need to have some programming languages to access and process it. And for that, Python comes in play. Another reason can be is sometimes you need to do data manipulation, meaning you need to compile two different data sets together. You need to break down on different pieces, and you cannot do it in SQL, depending on what databases you're using, but it's very easy to do in Python. Therefore, Python becoming more and more popular and useful for data analysis. So let's start with packages. I'm doing overview for Pandas packages, and as a first step, you have to import the tools you will be working with, and I'm just going to do a quick overview of those tools. So you will need to import NumPy, which is a very popular package for linear algebra. Pretty much all statistics are going to be through NumPy. Pandas, you're probably familiar with the Pandas as a main data processing package. I also will be using Seaborn, that's statistical graph package. That's really helpful for visualizations. We'll also be using Matplot, which is a plot package. Pandas SQL is very optional. I love SQL and I always use it in my EDA, but again, it's a preference. You might not need it, depends on your data set and depends on your objective. I also import in word cloud because I love playing with textural data. Again, depending on your data set. If your data set doesn't have any textural data, you don't need to do any NLP and you don't need to worry about word cloud. The stop words, it's like the last package. Again, it's an optional. It's an additional attribution to the word cloud. So what it does, it just helps you to remove prepositions, articles, not essential words, because they will affect your analysis. Okay, now I wanted to talk a little about plot styles. Because we're using Seaborn and we're using Matplot, we have a variety of different styles you can choose for our visualization. If you're going to ignore the step and not choose any style, you will end up working in a classic. You see on the right side here, classic. So in the way I'm doing, I'm usually picking between Bayesian method for hackers or between ggplot. I used to be an R user before I switched to Python. I still have preference for R packages and R visualizations, so sometimes I'm just using those because they're more familiar to me. Although Python has a lot of built-in different packages, and Bayesian method is a very popular. It's very simple. It has nice graphics, nice visuals. I highly recommend to use it. If you wanna play around with all those packages, you can just do print and to see all available styles. And here is a list of all those styles. Some of those are very similar. Some of those have small differences. Again, it's a preference, so up to you what you wanna pick. Yeah, this slide just to show you an example between different plot styles. On the left side, you see our ggplot style. On the right side, you see Bayesian style. The same data, pretty much the same thing, it's just slightly different visualization. Okay, let's talk about Python hacks. When you do exploratory analysis, there are 3 different areas you need to focus on. You need to focus on statistics, you need to focus on data manipulation, and you need to work with visualization. So we already covered visualizations part with you about plots, packages, styles. Now let's talk a bit about statistics. Those are first usually general comments which help you break down your data set into pieces and really understand what you're looking for. You have to try each of those to see how it performs with data. So you can apply the comment to the full data set, or you can apply a comment to a specific column. Okay. You should be familiar with some basic comments like max, median, describe. There are different variations for describe. You can specify a column name, then you will see information on specific data feature. Be careful with shape and D types. Depending on what data frame you're working with, it might not be tuple or series, so it might not work or will work. You always have to pay attention to null values. That's how you can extract null values and see how many gaps in your data. If you're working with Python, you have to work usually with indexes, so that's how to understand indexes and columns. These are, of course, not all commands, and you can explore Pandas to get a full list of commands, but those are essentials to start with. Okay, let's talk a little about feature engineering. As I said before, data must be cleaned before it can be visualized, right? Or before you can use machine learning, or before you can do any objective on it. So, to clean data, you need to be able to do any manipulations with it. So I have a way for you here to show how to read a file, or how to merge two files into one data set. It can be more than two files. You can have a series of different small data files which you can merge in one full file and process it. Or vice versa, you might need to break down that file into smaller pieces. When we do EDA, usually longest time we stuck is cleaning date times. Those can be very problematic to work with for visualizations, for example. So here I show you a way how to convert date into date time, or how to create a separate months column. Might be very helpful if you want to have a bar chart. Also about null values, that's one way to remove all values, or another way to fill in null values, depending on what you need to do. So you need to remove null values if you work in a specific machine learning algorithms, which can be very sensitive to gaps. You will have to fill in values when you can access these values somewhere else. For example, if you're working with age data in your data set, and there are a lot of users who don't have age value, what you can do, you can just get average age for a data set and then use this column to enter, to fill in empty values. Okay. Data cleanage also usually requires converting from one format to another format. Here is a way how to do it from variable into integer. Also, there is a way how to drop columns. You don't need to carry unnecessary data sometimes, so you can just get rid of it. And also a few helpful hacks really how to select your data and query your data for a specific week or day or month or season or so. Try those out. They're easy to implement in Python, easy to work with in Pandas, and hopefully it will speed up your EDA. Now, I wanted to review some of the common mistakes I see data analysts are doing. We already covered the first one, not cleaning the data. You really need to understand how many gaps in your data. If there's a lot of null values, it might not be significant to use, so you cannot really use it for any of your assumptions. So you need to spend some time cleaning your data. So just make sure the data you present to your stakeholders actually has high quality in it. Next concept, cherry picking. Very common, very biased approach. As a data analyst, you usually have your assumptions, a preference towards one data features and not another ones. I think the goal for EDA is to cover all data analysis, so make sure you don't do cherry picking. Make sure you're not focusing too much on one data feature and you're ignoring the rest of the data set. Next one is a way kind of similar. Don't focus too much on outliers. At the same time, do not ignore outliers. So if you're gonna follow my suggestions for statistical comments, you're already gonna have a clear understanding of outliers pictures in your data set. Okay, let's move on. Missing or ignoring data patterns. Yeah, that's a common one. Usually when you do EDA, your objective is to discover patterns in your data. But again, depending on the data set, you might not have clearly patterns which to stand out. So to give you some ideas, try to look for seasonality, for holidays, for weekends, for weekly patterns. As soon as you can recognize the pattern, you already can create a story. Next one is a very common mistake for beginner data analyst. Everyone loves visualizations, so I keep seeing how people put in so many unnecessary charts, which just overwhelmed reader, which makes your data very hard to comprehend. So sometimes less is more. Don't do too many charts, especially if they don't provide essential value. The last is the most important one, like an action. When you finish your EDA, it's a good practice to include a list of recommendations or hypotheses or next steps. Usually I see the step is missing because you already review the data, you clean the data, here is charts, all good. But that's not really the objective for EDA. Your goal is to give recommendation to your business stakeholders or to team leads what's the next step of the data. You're the one who should drive the hypothesis, what's the next idea we have to confirm based on a data set. So you cannot ignore this essential step. Let's move on. Okay, other exploratory tools and applications. As I said before, Python is only one of the ways to do it. And as technology keeps evolving, there are more and more different platforms which can help you to do your EDA. So on the left side, I have business intelligence platforms, which have data in some sort of already structured and built in, so you can just play around to understand it. You don't really need to use any Python here. Visualization charts on the central part shows most common applications which can help you visualize data. And on the right side are popular machine learning applications for which you're going to do EDA because you need to prepare data for machine learning. Interesting to know, try to play around maybe with some of those. But again, if you understand the concepts for EDA, it will be very easy to get started with any of those. Okay, to wrap up, I have some helpful links for you to review when you have a chance. The first one is my own EDA analysis in Kaggle. The second one is a very popular EDA in Python cheat sheet which you need to use. It has a list of all built-in plots, packages, commands, very helpful. The next one is visualization guides. So make sure you understand what the different types of visualizations are supported in Python, and make sure you understand which ones you need to use. And the real one is a reference to a very popular real Python domain, which has a lot of helpful tips. That's it. We're out of time. If you wanted to learn more or have specific questions, please feel free to reach out.
Hi, I'm Nina Zakharenko, a longtime Python developer and current cloud developer advocate at Microsoft, focusing on Python. And I wanted to tell you about 5 things you probably didn't know about Python. Here's one freebie. Did you know that Python is 30 years old? I know, right? And according to Stack Overflow, it's the fastest growing programming language. Now, there are a lot of misconceptions about Python from the early days that just aren't true. Things like it's only good for scripting or Python is only for the web. In 10 minutes, I hope that I'll change your mind. The first thing you probably didn't know about Python is that it empowers scientists and it drives discoveries forward. This is Concordia Station in Antarctica. It's extremely isolated. There's no sun for 3 months in a row, and it's the closest analog that we have on Earth to a base on another planet. This is a research facility that helps to study future deep space missions, and Python is used for things like reading sensors, processing data, visualizations, graphing, and charts for experiments. Experiments like drilling into ice almost 2 miles deep to analyze air that was trapped 1 million years ago. In a keynote given at EuroPython in the summer of 2019, the scientists shared that they used Python all day long and that they use it for most of their programming tasks. That means that Python might help us live in space one day. Python is also great for data science. It's used to process massive amounts of data. It's helped in breakthroughs all over the world, such as this one in gravitational wave astronomy. Python was used in a variety of ways, from operating the detectors to analyzing massive amounts of data to pushing alerts to astronomers and sharing the results. And there are a lot of incredible open source tools like Jupyter Notebooks, Pandas, NumPy, SciPy, PyTorch, that are tools for AI, machine learning, and scientific pursuits. 2019's Nobel Prize winner in economics, Paul Romer, uses Python for his work. He has an excellent blog post where he talks about how the open nature of Jupyter Notebooks drove the project to success ahead of its proprietary competitors. And he says that in science, anyone can experiment. In open source, anyone can access the facts of the code. Python is also used to create incredible games and art. EVE Online is a massive multiplayer online game that is set in space, and the client and server code were written in a variety of Python called stackless Python with lightweight threads. There were hundreds of thousands of players during its peak popularity. One of EVE's creators said that Python enabled us to create EVE Online, a massive multiplayer game, in record time. The flexibilities of Python have enabled us to quickly improve the game's experience based on player feedback. This is Super Potato Bro. It's a platformer, and the whole thing is written 100% in Python and Pygame. You are a baked potato fighting against an evil ladle who's trying to kidnap all your friends and turn them into soup. And you can buy this game on Steam for $4. Processing is an open source language that's geared toward visual art. It allows you to create incredible animations in Java, but thanks to Jython, which is an implementation of Python that is designed to run on the JVM, and an open source project called processing.py, you can write code for processing entirely in Python. Python can also control your connected home. Everything from your lights to your vacuum cleaner to your internet-connected rice cooker. Yes, that is a real thing. Thanks to the Home Assistant library. This is an open source home automation library that puts local control and privacy first. And we all know why privacy is important these days. It's written in Python. It is powered by a worldwide community of tinkerers and DIY enthusiasts. It currently has 34,000 stars on GitHub, which is an increase of 16,000 stars in just a year. And it's perfect to run on a Raspberry Pi or a local server. There are incredible dashboards and integrations. Now, this one you really might not have known, but Python can scale. As an interpreted language, it can be slower than others, but some advantages outweigh the disadvantages because it's easy to write and it's easy to read. And that means that development speed can progress more than performance. Instagram just hit 1 billion active users in 2019. That's billion with a B. And it is the world's largest deployment of the Django web framework, which is written entirely in Python. Python also powers the backend and the client for Dropbox. Guido van Rossum, the Python creator, had worked there since 2013, and Dropbox engineers write blog posts that highlight how they can optimize Python for performance. Lately, they've moved a handful of performance-critical services to other languages, but that doesn't mean that Python is going anywhere. They said that if Python didn't work at scale to begin with, there would be nothing to improve upon because Dropbox wouldn't have lasted long enough to even face this problem. Companies use Python to different extents, and a lot of them have an incredible amount of users, and apparently they all like the color red in their logo. Quora had 300 million monthly uniques in 2019. Netflix relies on Python to power its data analysis on the server side, as well as a few other use cases. Surveyed Netflix engineers cited the standard library, the active development community, and the rich variety of third-party libraries as the biggest advantages to using Python. Reddit has been built on Python since 2005 and has more than 500 million unique visitors every month, making it one of the top 5 visited websites in the US. Now, Many people know that Python can run on a Raspberry Pi, but did you know that there's a whole ecosystem of interesting hardware platforms that run Python? There is MicroPython, which is a lean and efficient implementation of Python that includes a subset of the standard library, such as the interactive prompt, list comprehensions, exception handling, but it's optimized to run on microcontrollers, and it can fit and run with just 16 kilobytes of RAM. CircuitPython is an Adafruit port of MicroPython that is focused on education and ease of use and learnability. Both of these projects are open source and very active. This is a Adafruit Trinket M0. It's a tiny microcontroller board that's as big as a quarter, and it's low cost. It's under $10. There's a Cortex M0 ARM processor, which is one of the smallest ARM processors available, and it ships with CircuitPython support straight out of the box. This is another product that I'm a big fan of. This is the HoloWing. It's a spooky development kit with some extras like a full color screen, a light sensor, a speaker, a LiPoly battery charging port, an accelerometer, etc. The 4 fang teeth are analog capacitive touch inputs, which are pretty cool. And there are tons of other hardware platforms focused on education that run MicroPython, like the BBC Microbit, which was given to every 12 to 14-year-old in the UK in 2016. With Python, you can create incredible wearable projects. I made these earrings that I'm wearing using Adafruit Gemma M0, some WS2812 LED rings, and a tiny LiPoly battery. So my earrings run Python, and the code and the circuit diagram for these earrings is available on GitHub at git.io/pyearrings. I think there's really no time like now to try Python. It's improving with every new release. Python is open at its core. It consists of an incredibly friendly, welcoming community, and there's no time like now to take the leap. If you can even contribute back to the language. To learn more about what Microsoft is doing with Python, you can check out the link, nina.to/manning2020. And thank you so much for joining me. If you'd like to stay in touch, please follow me on Twitter at @NNJA. Thank you.